So hopefully everyone's had time to move in from next door. Thank you everyone for coming to this session. I'm Deborah Jones and I'm one of the knowledge transfer managers at Innovate UK Business Connect, and I work on our SAF innovation programme. I have a background in catalysis and synthetic fuels. And one of the reasons I wanted to run this session, in the role that I do, I work with a lot of small companies who are looking to scale. And they come quite often from a slightly different sector, and they've pivoted into this sector. And we've been trying to work with them, understand their challenges around their technology and integrating their technology into the supply chain. But we're also hearing from other sources as well that the only barriers to scaling SAF in the UK are around energy prices and financial support, investment and policy. And I don't necessarily think that's true. I understand some of those are all issues, and they're really important issues, and they are things that are stopping us from getting us to where we need to be. But a lot of those are outside our control as an industry, and I wanted to try and understand where there are opportunities for us as an industry to make a practical difference to scaling up SAF in the UK. So we'll be hearing this morning from firstly a presentation and then a panel discussion from organisations who are actually already making SAF in the UK and around the world, and they're building and licensing technology for first-of-a-kind plants across the world. So we've already heard about some of these areas yesterday, and this slide is fairly crude, not exhaustive, also not to scale. Just point that out before anybody comments on the size of my plane and my boat. But I guess what I'm trying to highlight here is that we're really trying to build quite a complex supply chain. For example, there's 42 feedstocks recognised under the ICAO CORSIA. Not all of them are applicable to the UK, obviously, as we've heard yesterday, and there are 11 approved processes with a further 11 undergoing evaluation, and 122 airports worldwide who are distributing SAF received through a variety of different ways, including tanker delivery and pipeline. So, like I said, fairly complex supply chain, and then you've got these underpinning things like investment, policy and regulation, and also infrastructure. So without further ado, I'll hand over to Paul Hubbard from Fulcrum Bioenergy, who's going to share some of the highlights and the lessons learned from the construction of their first-of-a-kind plant in the US, and how that's impacted the ongoing plant development in the UK and elsewhere.
Good morning, everyone. I'm going to talk a little bit about the Fulcrum project in the US, the implications that project's had on the Fulcrum project for the UK, some of the differences, some of the lessons learnt, and give a general overview of how we're looking to scale SAF. So, very quickly, Fulcrum Bioenergy has completed the world's first municipal solid waste to liquid fuel production plant in the world at scale, at a commercial scale. It's been a long time coming. The company was formed in 2007, and as you'll see there, we didn't achieve first fuel until 2022. So it's a gap of 15 years of development. So the project in the US is in Sierra Nevada. It is a single gasifier project. It gasifies what we call an engineered feedstock, which is a feedstock taken from municipal solid waste. It's very similar in nature to what we call in the UK RDF, so refuse-derived fuels. There are some additional processing that we do before we put it into the gasifier, that it differs from the commercially available RDF that traditionally goes to an energy waste project. But they're, all intents and purposes, they are very similar. So we have slightly different requirements on components. So if you're used to seeing RDF, you're used to seeing the feedstock that we create in the US. The size of the project in the US is 175,000 tonnes of engineered feedstock fed into the gasifier a year, and that produces 11 million gallons of liquid fuel product. Now, they are both US numbers, so it's US tonnes and US gallons. The project in the UK will be 500,000 tonnes and will produce 100,000 tonnes of SPK. The difference in the US, we do not upgrade at the site at the moment. So we produce Fischer-Tropsch liquids. That is then sent off to another refinery for co-processing. But all intents and purposes, this is a very similar plant to what we're looking to build in the UK. First fuel was achieved in 2022, which was a big thing for us because that's where we proved that the concept worked. We then had to take that first fuel and have a sustained run and prove that we can produce fuel over a period of time. That was done during 23. What we highlighted or what we identified doing those or achieving those two targets was that there was a number of areas of the plant which were not robust enough for a long-term sustained production run. Essentially, the project, we drove it to identify all those failures. Over the last 6 months, we have been working on a whole series of modifications, changes to the plant, changes to the configuration, changes to equipment, improvements to that robustness. They have all been implemented, and we're in the final stages of closing the plant up, doing the final inspections, so that we can go for a new test run this period of time. So I was hoping to come here and say that we'd already started that, but unfortunately we were a little bit delayed. We were hoping to start by the end of April. It's now looking like we will do that startup during May. And the intent is then to do an extended run so that we can now then prove the robustness of the process as well. Further at the US site, we are then going to shut down again and install upgrading. So we no longer export the FT liquids, but we will do the full hydrotreating ourselves on that site. Just a quick run through of the process for those of you who don't know. It's a gasification process. So we gasify the MSW. The gas is then sent through a gas cleanup. We then have the FT liquids. We then hydrotreat, and then we export an SPK. So the synthetic kerosene that is then blended with fossil at a ratio of up to 50-50. More likely in the early days because it's going to be so rare and we want more product to get out to the airlines. It'll be at a lower ratio, maybe 10%. But the fuel standards allow you to blend up to 50%. And then, obviously, once it's blended with that fossil, it becomes a certified SAF. If I just go through some of the differences that we have between the US and UK projects, if we ignore for the moment the regulatory differences in how you account for life cycle GHG, because that depends very much on the region you're in. In the US, you're allowed to offset against landfill emissions. In the UK, that offsetting doesn't happen, so we have a very different way of calculating what the life cycle savings for the SAF are in the different regions. So if we stick to the physical, in the US, the waste management market isn't quite as mature. So Fulcrum runs all their own MRFs. And all the future projects in the US will also have their own MRFs. In the UK, we're looking to break into the existing waste management process, waste management business line, and take the RDFs that we talked about earlier into the project. That's probably the key difference between the two locations in how our projects are going to work. In order to minimise technology risk, in order to minimise transfer of the project from the US to the UK, we are keeping all the same licensors. We are keeping all of the same process, so the process island remains the same. And that's the manner in which we're going to be able to scale up slightly quicker, rather than trying to have to prove new technologies in each location we go. The scale-up risk is being addressed by, as we saw in the US, we have a single gasifier. In the UK, we are looking to use 3 gasifiers, but they are 3 gasifiers from the same licensor, of the same scale, the same capacity, the same dimensions. We are combining those 3 gasifiers together once it leaves the gasification island into a single train. That is where we're going to get the economies of scale. Once you have got the syngas from the gasifier, all of the processes downstream, they've all been proven at much higher capacities than we need. So when you look at the syngas cleanup, you look at all of the ancillary and utilities around that area, you look at the Fischer-Tropsch unit, you look at the hydrotreater, you'll see them all around the world in every oil and gas refinery, and they've all been proven at higher throughputs, higher capacities than we need. So there's the technology risk with all these projects is in that front end. So we're avoiding scale-up risk and technology challenges by keeping the same that we have just proven in Reno. So that's key for ourselves in how we can get these projects up and running quite quickly. We also have a book of lessons learned of everything we have done in the Reno project. We've identified a whole number of shortcomings, a whole number of areas which needed improvement. We've worked through those. We have got our technical solutions to those. Unfortunately, they're commercially sensitive, so I can't share them with you. It is our advantage on over the market is how we're going to deal with those. But our feed project for the UK is incorporating all those lessons learned at the moment. Our feed for the UK is 50% of the way through, due for completion the end of September. But if you look at the statement I just made, that where we're trying to avoid scale-up risk, where we're trying to avoid the technology challenges, and the fact that we're keeping the gasifier the same as what we've just completed in Reno, but we're willing to scale up in a single train the rest of the plant, I think you can guess where the problems for the early plant were. It doesn't take a genius to work that out. So if you are looking at lessons to be learned, pay careful attention to the quality of your feedstock coming in. Pay careful attention of how you get that feedstock into the gasifier, and pay careful attention to the syngas coming out and how it goes through its initial cleanup. And that is essentially where those lessons are. But again, I can't go into specifics as to the actual items that we've had to modify. Other areas that we are looking at to help us to scale and to get the SAF industry moving is we are looking at modularisation. So we're looking at how we can modularise these plants, build them in a central location, get them shipped out to the various areas that we are looking to operate in. So with that, we are looking at how we can dual certify, dual code, so we can have the European PED plus the ASME code certification for vessels, what that does to us in terms of wall thicknesses, and is it worthwhile doing that? But that's another area we're looking at to standardise our equipment supply across multiple jurisdictions. Other areas that we obviously need to look at is where we choose to put these plants. So we are looking at areas where there's supporting infrastructure. We're very lucky in the UK in the infrastructure in the location we are looking to be in. It's the Ellesmere port area of the UK. It has a hydrogen project going forward, or very near to FID. It has a CCUS project in the area. It has all of the utilities that we require in terms of wastewater. It has electricity supply, gas supply. It's an industrial area. It's used to dealing with these high demand projects. And most importantly for Fulcrum, other SAF producers have other issues. It has waste availability. So it has 2 or 3 large areas that create the waste that we need to be able to take. So we have the Manchester, Liverpool, Chester triangle of waste arisings. So that's another area that we need to carefully look at, how you get your waste into the site and then how you get your product out. Another area that we have, we looked at quite a lot when we were choosing the area we wanted to be in, was how could we take road transport off of the, or export product off of the roads. We're fortunate the area we've chosen to be in has access to the Manchester Jet Line, which will enable us to take our product direct to Manchester Airport without using road transport. Again, helping the GHG score and the overall environmental benefits for the SAF project. I think I could talk for a lot longer on the project, but I'm conscious we have a panel to get through as well. So I think I'll end it there. But if anyone wants any more information, I'm here all day. We have a stand outside, and we have the Fulcrum team here as well. So I'm not here on my own. So stop by, have a chat, ask your questions. We're happy to answer where we can. Okay. Thank you.
Sit down, Apple. Great. Great, thank you, everybody. So as Deborah introduced and as Paul said there, we're kind of entering now on more of a panel discussion. We'll kind of talk a bit more about the themes, but hopefully have a bit more time for introductions as well. So thank you very much, Paul, for that excellent presentation, really interesting. By the way of introduction, Paul did a great job of explaining the benefits of the Ellesmere Port area, and that's actually my heartland. I live locally there. I'm a project manager for Progressive Energy, but very much involved in the HyNet project, which that was where Paul was alluding to in terms of integrating their next plan, one of their next planned developments. So that's my role in terms of that. That's integrating not just SAF, but other emitters, other hydrogen users. So I've got a broad understanding of SAF. So I'm actually in quite a good role here. I know enough information to be dangerous, so I might just ask some relatively ignorant questions, but hopefully the panelists can help me out a bit. So obviously Paul's given a very good introduction to himself. I'll let the panelists introduce themselves, but we've got Zainab Yacoub from Haldor Topsoe, we've got Candice Carrington-Hughes from Petrofac, and we've got Simon Holt from Phillips 66. But I'll let them introduce themselves and their businesses in turn, so thanks.
Thank you. My name is Zainab Yaqub. I'm a Senior Licensing Manager at Topso. So my role involves business development and licensing of SAF technologies. A little bit about Topso and what we do. Topso is headquartered in Denmark. We provide technology licensing and catalyst solutions to project developers. We have a great and a fantastic diverse portfolio of SAF technologies. We are a market leader in HEFA pathway. We also have the PTL route, which is basically hydrogen and CO2 feed. First thing, I think we have the Power to X, we call it, is our SOEC, electrolyzer technology. Our partner or co-licensor, Sasol, we work with them on the Fischer-Tropsch pathway. We also have, we are actively developing methanol to jet route as well. If you'd like to know more about any of our technology lineups, please come find me. I'd be really happy to talk to you about those in the break.
Okay, hi there. I'm Candice Carrington-Hughes. I'm a Senior Refinery Consultant at Petrofac. I've been blessed, actually, in my over 20 years of experience in the petrochemical and refining and energy transition industries, to have worked from a few different perspectives. So fuel producer, licensor, and now engineering contractor. At Petrofac, we're probably quite well known in the oil and gas as an oil and gas EPC, particularly in offshore. But over the past 5 years, we've done a huge amount in energy transition, working in the various verticals, so carbon capture, utilization and storage, waste to value, hydrogen, offshore wind, and also residual energy. I'm based in the Woking office, where we do a lot of our studies, feed, and some small EPCs, and we're helping a variety of clients right through from licensor, technology owners, clients, as well as some of the larger producers to find the right technologies to be able to realize their SAF targets. So I'm really delighted to be on the panel today and hopefully give, from an EPC contractor's point of view, the lessons that we've learned and what we think will be quite helpful in delivering SAF in the UK.
Good morning, everyone. My name is Simon Holt. I work for Phillips 66. I think we have 2 L's and 1 P, but never mind. I've worked for Phillips 66 for 25 years, started my career at Humber Refinery in North Lincolnshire, and worked in a variety of different roles, spending time in Houston, and I now head up our emerging energy department in London, where we work on a variety of different energy transition pathways, but our main focus is on renewable fuels. We've been processing used cooking oil at Humber Refinery since 2017. Been processing tire pyrolysis oil at Humber Refinery since 2020. Been supplying SAF to British Airways, as was mentioned previously, over the last 2.5 years. And so we're continuing to develop new pathways, very much focused on co-processing at Humber, but also developing independent projects as well for the UK. Phillips 66 is a big US company with 10 refineries and gas gathering, NGL processing in the US, and we've just recently converted our San Francisco refinery, 50,000 barrel a day refinery, into a renewable fuels facility, making renewable diesel today, but we should be making SAF by the end of the year. But that's, yeah, so everything we're producing today is HEFA based, but I think that's currently where the market's at, but we're looking to see other projects develop.
Excellent, thank you. So echoing Deborah's comments right at the beginning, I suppose where we're trying to focus in within representatives of hopefully quite a diverse portfolio of supply chain perspectives is actually what can we do as a supply chain, from anything from an operators to experience to licensors and consultancy, but more than that from your experience as well. So understanding what we can do and not necessarily get stuck too much in the weeds of the legislative, which we are completely aware that is a big factor. So if the conversation does go that way, I won't stifle it, but our goal is really to focus on what can we do ourselves to get this going and to get the supply chain ready. And I suppose leading on from that, and it was a kind of building on your presentation, Paul, it was great to hear around the you scaling in the US and the lessons learned, where you say primarily at Feedstock. And actually, I have a background as previously as a commissioning engineer working for a licensor, and I can relate to Feedstock being an issue for sure, and understanding those lessons learned. As you said, you're keeping the same supply chain together. I suppose, probably building on Paul's presentation, I'd probably like to invite the other panelists in to get their opinion on what are lessons that can be learned, that things are happening internationally, what can be brought into what we're doing in the UK and beyond. Probably, I suppose, Simon, from your perspective, would you be able to kick off any thoughts?
Yeah, I mean, there's obviously a huge amount of work going on across the globe, and you know, I think the UK was leading the way, and you know, I think we've always, as a nation, done a great job in developing technologies and scaling up from lab scale. But I think what we're seeing now is that other countries are you know, stealing the march on deploying technologies at scale. And you know, it's still early days, and you know, I don't want to be too down on the UK, because I think hopefully we'll get to the you know, the plus points that the UK brings to investors in SAF shortly. But I think we can learn from the projects that are being developed in other parts of the world, and certainly as a US company, you know, we look at the US and the UK as very stable economies, stable politically as well, and as we develop our SAF projects, we're looking at scale, and you know, it's not just a case of 10,000 tons here, 10,000 tons there. You know, we're looking at multiple hundreds of thousands of tons to get the economies of scale required. And so I think a company like ours can certainly learn from the projects that we're developing in the US. I do tend to think that we will see these large-scale projects built in the US ahead of Europe. And I'm starting to hear that, you know, China is developing as well some SAF projects, but I think there's many learnings that we can take from how they've approached that and use the benefits of the landscape in the UK to support the deployment of those types of projects at scale. But we may have to rethink a little bit about the types of projects that we need to develop and deploy in the UK to get the scale that we need and the economics and the certainty for investors.
Oh, that's excellent. Candice, how does that fit with your kind of perspectives on the lessons that we can draw on from current active SAF projects?
Yeah, no, I agree. I agree completely. I think there's a lot that we can learn from other projects that have, you know, progressed and sort of see where they have met some challenges and hopefully learn from them. I know a lot of the information is quite commercially sensitive, naturally, but I think that there's still ways in which that we can work through them. Obviously, the ones that have got the jump, technology providers that have proven their technology, you know, working with them, that will be a really good way of that knowledge transfer. But I wanted to pick up as well on something that Paul mentioned in his presentation about, you know, they formed a company in 2007 and then had first production by 2022. So I think for me, one of the key things is starting. So, you know, even I see a lot of projects, and we see a lot of studies and a lot of ventures that try to do quite a large scale, and we certainly do need that. But I think that at least just starting, because it's when you start, that's where you can investigate and find a lot of the pitfalls. We'll probably at some point touch on heifer. I mean, it's quite a big part of SAF. But I can think back to my time previously when I worked with a licensor, EOP. 10 years ago, we were starting to deploy that sort of technology. And I think it's through being able to get it out there and get it operating. And even if it's just as co-blending, even if it's just at smaller scale, the more of those technologies that get up and get started, that's where you can find where all the pitfalls are. And through operating over that time, that's where the confidence grows. And then now that we're trying to deploy it, we have heifer, and it's the same way. So things like what Fulcrum Bioenergy you're doing, that will increase the confidence in that technology. And then we will learn, but it's through starting. So I think for me, a big thing is helping to support smaller outfits that are using novel technologies to get started.
Excellent. I suppose what I quite enjoyed your description, Paul, in your presentation of the Manchester, Liverpool, Chester triangle, slightly different than the Golden Triangle that's in the northwest at the moment, where the footballers live, but nonetheless probably key. And I suppose moving on from those general challenges, and I think Simon touched on this. I suppose what do you see? I know I'm aware of the confidentiality side, but I suppose on a like-for-like site within the US and the UK, what do you see as the challenges of developing a project in the UK? Are they the same, or are there subtleties that are different?
Yeah, there are subtle differences. The variability of waste is key for us. For our process, obviously we have MSW. And the difference in waste between the US and the UK, you think of waste as waste. Unfortunately, it isn't. In the US, you have a single waste collection. In the UK, we now have, I don't know where everyone lives, but every week I have 4 different bins to put out. I have a food waste collection, I have a plastics collection, I have a paper and cardboard, and then I have a general waste. And then if you add in the green waste as well, your green bin for your garden waste, which comes every other week, you can see that the contents of your waste bin in the UK is very different to the waste bin in the US. So our plants have to be designed to cater for both aspects, and for those areas where people aren't quite as good at recycling. So just because where I live we have those bins, other councils don't do all those different collections. So what turns up at our gate on a daily basis is so different from what turned up yesterday, and that is a key difference between us and the US. In the US, there is one bin and it always turns up pretty consistent. In the US, in the UK, because we do so much recycling, we're seeing in all our testing a lot more variability.
Excellent. And I suppose moving that on from, as a licensor, Zainab, you must see quite a lot of different projects around the world with different challenges as well. I suppose from the UK context, how do you see the UK different from the rest of the world, or the same, or having your view on that as well would be great.
No, that's a very good question. And I was going to say, as a licensor, we see multiple projects, right? Multiple locations. The UK, I have to say, is leading in terms of the municipal solid waste to SAF production. 3 or 4 projects in the UK, one being Fulcrum. So it's exciting. In the US, however, what we see, a lot of heifer co-processing, simply because there is a lot of refining capacity. Co-processing is a small change in the refinery, or small or big, depending, but you can still add SAF. So I think that's what we see as a licensor, a big difference in the 2 regions.
Excellent. And I suppose it's probably coming back to the point that you were saying before Simon, around going back to UK, what would you see are the UK's SAF strengths, kind of building on these differences as well?
Yeah, I think it's important to look at those strengths, and you know, Paul touched on it on one of his slides. You know, the UK has plans to have 4 industrial clusters by 2030. So there's going to be CO2 capture, storage, transportation and storage infrastructure in the ground this decade. There's going to be green hydrogen being produced this decade, fairly small scale, but you know, again, the government's got big plans to ramp that up. So I think most of these SAF projects need access to CO2 capture and green hydrogen. So I think the UK is going to massively benefit from that. And you know, in our conversations around Humber Refinery, you know, we're hoping to be part of the Viking cluster. And you know, the number of companies that come to us and say, well, you know, we're interested in developing SAF projects close to you. You know, which is you know, really encouraging, and I think you know, it's going to happen in each of those four clusters as long as they get built. And I was at a conference last week. It was the North Sea Decarbonisation Conference, and you know, not just the UK, but you know, that kind of North Sea basin and the countries surrounding. There's so much renewable energy that can be used, and you know, thinking ahead to the 2040s really is when I think we're going to see eSAF be deployed at a much larger scale. You know, the North Sea region in itself, and the UK is a big part of that, has got a huge part to play in it. And you know, as we heard from British Airways and others, you know, Sustainable Aviation Group, you know, that they need that industry needs e-fuels to be deployed at massive scale. You know, there's obviously an energy question about, you know, do we have enough energy and the intermittency of all that, and that needs to be dealt with. But you know, there's huge potential for e-fuels, and I think the 2030s with waste to SAF and the role that the UK can play, I think that's just a stepping stone to the ultimate goal. So yeah, and just going back to the US, you know, I think we're going to see ethanol to jet facilities built in the US, just because they have a lot of ethanol and you know, it's crop based. But again, I think the UK and Europe can learn a lot from those projects and the scale up of the technologies to the type of scale we need.
Excellent. No, I from my perspective, representing one of those 4 clusters as well, a different one within HyNet, I can definitely echo that of the attractiveness of the infrastructure being put in ground, attracting other interest in there. I can definitely relate to that, and I think that is definitely where the efforts and sincerity of the government through Department of Energy Security and Net Zero has then brought up this, and I could definitely see as a growth point.
Can I just add one point? We kind of underestimate the role that government plays in the UK and the collaboration between industry and government and how open they are to ideas, suggestions. You know, the consultation processes are very good in my opinion, and they don't really have that in other parts of the world, and not in the US. I mean, the US is too big to really do that on a federal scale.
Yeah, I could only underline what you just said there. It's absolutely aligns with our experiences as well. They've done a fantastic job, and actually not just even at the local government level, the support of it, they can actually see the way forward to get it through. And I suppose that is highlighted, as you said, within that first step. The key is part of those first 2 leading clusters with aims to take an FID this year, which I suppose probably brings on to a different point around FIDs and financial investment decisions for different developments and different projects. And probably starting off with Zainab, what do you see are the key challenges to reach FIDs for all of these projects, and your thoughts on how technology plays a role within that?
So as a licensor, we would love for projects to take FIDs. And many regions around the world are introducing SAF mandates, which is great because the industry needs some kind of an investment certainty. However, I believe this is it's not enough because every project, in fact, the first couple of projects carry a big risk. There's feedstock risk, off-taker risk, construction risk, and we need to do more. As a licensor, what we are doing is we have bankable technologies. So like I mentioned earlier, HEFA is a more mature technology. Coming onto the Fischer-Tropsch pathway, the e-fuels, as we call it. Yes, the front end, which is our e-react technology, is not commercial. However, the back end, which is the Fischer-Tropsch and the hydrocracker, when we partner with Sasol, the big GTLs are operating in Uzbekistan, in Qatar, in Nigeria. So that's a super bankable pathway. And we have a good technology wrap. We are willing to work with our clients on how we can make the projects bankable and then help them get to FID. I think also we mentioned earlier about how the UK government, I think the big step up is the revenue certainty mechanism, which I think helps, and I think will play a big role as well in helping these projects to get to FID.
That's incredibly interesting, and I'd like to bring in Candice and your thoughts on this as well.
Yeah, so as an engineering contracting company, we are also very interested in our clients reaching a FID. I think that, yeah, there's certainly, I agree, those challenges around supply and off-take agreements being put in place. Sometimes the technology itself can pose a challenge. Technologies like HEFA, very well understood, very advanced. Fischer-Tropsch technology has been around quite a long time, so there are a few bits around the front end. But there are other technologies that we are still seeing some challenges with, and certainly Paul's mentioned in gasification through, some of those chains in the pathway. There are still some issues that need to be worked through. But I have no doubt whatsoever, and I have full confidence that the technology portion will be worked through, because it's a matter of getting it on the ground, getting it up and running, and then, relying on our strengths, our innovation, our intelligence to be able to find and troubleshoot these issues and work through them. So I think once we get started, the technology issues, those will be, fairly relatively minor compared to some of the other challenges. As an EPC contractor, I'd say some of the key issues we see with our clients face that seems to prevent them from getting to FID. A big one, and I hate to keep talking about it, is money, is capital. So often that upfront investment may be more than what they initially anticipated. And once you've gone through an initial concept study, you raise funding and you attract investors. But then once you go through to a substantial level and you conduct a feed study and you understand what is needed in the ancillaries, or perhaps additional redundancy to give more confidence to investors that your on-stream factor will be sufficient to meet your obligations, your contractual obligations. That cost builds a little bit more. And factoring that in is sometimes a bit of a challenge to then go around for additional investment and bring other investors on board, because it's all about minimizing risk. So I think that early engagement with key stakeholders. So obviously for myself, I'll plug for EPC contractors, for engagement with licensors, engagement with investment funding, permitting bodies. I think early engagement with all these key stakeholders is really important so that you understand and get a full picture of what are the steps that you need to go through and what are the challenges that could be faced. So I think that will help quite a lot in bringing through. Another one that I wanted to say as well, particularly as an EPC, is I know that there's a lot of residual risk within that EPC construction phase. And it is quite difficult. Many people ask us, would you consider doing a lump sum turnkey on a renewable project? And I'd say that in the current landscape, it is quite difficult, and that is quite tricky. But there are creative mechanisms that we can employ to help through that EPC phase and help manage the uncertainty and the flexibility that's needed there. So again, early engagement is really quite key to speak with the key stakeholders.
Sorry, can I just add to what Candice said? I think there's from two speakers, what I learned yesterday from Martin, he mentioned that there's many MOUs, there's many LOIs. We are yet to see a long-term offtake agreement, right? And then this morning's presentation on partnerships and collaboration, I think it's really important because we need to identify the risks in a project and allocate the risks to the appropriate stakeholders.
Mm-hmm.
That would help us move the projects and get closer to FID.
No, really interesting comments, and I suppose it's all part of that journey that you mentioned before around how you initiate, how do you start to get things going, how do you get the scale right to de-risk that. And I suppose that was one other topic area I was generally quite interested in terms of the scale up, and I was really interested to probe a bit more in what you said, Paul, about modularization, as much as you can, obviously, and a bit more about those scale challenges around, say, feedstock availability. You kind of alluded to as one of the challenges, but not necessarily just limited to waste, other feedstock availabilities and utilities. So probably, if you don't mind starting, Paul, as that scale challenge.
Yeah, so the scale challenge is an interesting one. So I've spent most of my career in oil and gas, and you tend to build the largest plant you can get away with. Having moved to waste to fuels, you're limited by where the waste arisings are. We could go larger than the 3 gasifier unit, but getting hold of that amount of waste in one area is very difficult. And when you start talking to local communities about shipping waste into their area, it's not a comfortable conversation to have. So you're really limiting the scale of the projects at the moment to the waste arisings in that area. So we have calculated that a 3x is probably the optimum size that we can do at the moment. Now, in the future, we may be able to go larger. We may find that we can bring additional waste into an area. But at the moment, that is our limiting factor.
Excellent. And I was quite interested, Candice, with your point around clients always asking for the lump sum turnkey perspective of that, but in the context of scale with that, and how does that fit from an EPC perspective? What would you see? Would you agree at 3x would be a good route which fits the sort of the local environment and the kind of scale need, or would you have a different perspective?
Yeah, so I think it varies, right, depending on the pathway that you're looking at. And I think that it depends on the particular ambitions or the particular structure that the client has. So for Fulcrum Bioenergy, they obviously have that structure where you want to receive the waste, process it right through to the SAF. So in your plant in the States, you're producing the liquid, and then that's your product that you're sending to refineries, and then eventually you'll bring that in so that the whole SAF itself will be produced by itself. So I think it depends on how it's structured, and perhaps for those that are looking to do right through to the end product, that sort of scale may be, it certainly does need to be tailored around the availability of feedstock. But I'd like to say, we've had experience with looking at various pathways. So whether it's gasification through Fischer troughs to SAF, whether it's HEFA, whether it's e-fuels using, again, Fischer troughs, methanol to jet, alcohol to jet. There are a lot of different pathways that can be used. And of course, I'd like to also raise other types of oils, so pyrolysis oils. And one that we're quite heavily involved in, even a sewage sludge using a biocrude generation to make you're making your SAF through hydrotreating upgrading. So lots of different pathways that are available. And it depends on what's the source of the waste that you're using or the feedstock that you're using in the case of green hydrogen and CO2, and what strengths you have in that particular area, what pathway you want to use. There might be a case for dividing that pathway a bit and having a portion of your process happen close to the source of the waste, and then having that then transferred and upgraded or then further treated where that makes sense. And that could depend on existing facilities or availability of closeness to where that would be processed. And I'll give an example. So James Highgate yesterday made a presentation of the Firefly project, and he spoke of a hub and spoke model. So in that case, they were looking at using sewage sludge from anaerobic digestion water treatment plants, making a biocrude out of it, and then treating that biocrude to making sustainable aviation fuel. However, instead of having one large plant where you do everything all together, the model of that would be, as he mentioned, a hub and spoke model. So locating the crude oil generating close to the source of the waste, so close to the water treatment plants, and then having that biocrude transported to a centralized hydrotreating mini refinery. And that is a model that can work for potentially other types of pathways. I could think of things like tire pyrolysis and plastics refining as well. And in that model, you can also make use of existing infrastructure, which is actually one of our strengths here in the UK. We have a lot of different types of industry that have been going for over 100 years. So refining, petrochemicals, waste to energy, exploration, renewable energy. So we can also make use of some of our existing infrastructure by that sort of model. And I think it just depends on what pathway you're looking to support, whether you scale it up in that one location or whether you scale it up by having a sort of a distributed model.
That's really interesting. And that probably just brings Simon in on that point as well, because I think you referenced that you're kind of doing one production method now and you're looking at others and generating that. I suppose it's exactly what Candice was talking about, really, but what are the challenges that other production routes that give as they scale up, and do you see sort of synergies from other sorts of different technologies that you currently employ that can be used, I suppose?
Yeah, I think it comes back to Candice's point about infrastructure and also minimizing costs of projects. And I'm clearly biased because we have a pretty sophisticated piece of kit already in the ground that's been operating for over 50 years, and we believe it's still going to be needed for a few decades to come. I mean, one aspect of Humber Refinery is that it makes a huge quantity of synthetic graphite material, which is used in lithium-ion batteries, enough to supply over 1.3 million EVs a year. So that type of material is going to be needed for a number of decades, and so that's part of the reason why we've gone down the path of co-processing and carbon capture and refueling our heaters with hydrogen to reduce our emissions, scope 1, 2, and 3. But one thing the average person on the street doesn't appreciate, that the UK has a a very extensive and interconnected network for jet fuel supply, which came out of the Second World War, now owned and operated by Exolum and connecting many airports in the UK, storage tanks, and so co-processing or standalone processing through a refinery like ours, test and certifying existing storage tanks. Storage tanks are very expensive to build. Pipelines are expensive. You're probably not going to get permitting for them. So, you can deliver into airports today. Delivering the SAF we produce at Humber into Heathrow Airport. That for us, aviation hasn't been a business for us. We make heating oil, but the partnership with British Airways enabled us to think differently and produce a SAF, heifer-based, admittedly, but we could supply directly into Heathrow airports using that existing infrastructure. So I think we need to think more about that, how we can reduce the costs for projects to get them to FID.
Excellent. And Zainab as well, what do you see as the differences between the different production routes and understanding what you can bring from existing technologies and the like to benefit SAF production?
So all the very relevant points from Candice and Simon. I think we need all pathways. Will PTL or e-fuels play a significant role in decarbonizing the aviation and making more SAF? Yes, but will it do now? No. I think we have a few years to go still. It's not going to be a dominant pathway now. I think the first wave of SAF will come from low carbon sources as opposed to carbon neutral sources. So again, have a pathway, very mature. The gasification-based routes, municipal solid waste to SAF, as I said, is gaining popularity. So that's something that I think will fill up the SAF over the next few years.
Excellent. No, really useful. And I suppose where I think I'm moving slight change of direction now would be picking up a bit of Simon's point, but I might start with Paul first actually. But in terms of where we're going with my experience, and this is a very selfish question that I'm about to ask, is my experience from a HyNet perspective has been very much involved in carbon transport and storage, business models, contract for differences, and much the same with the hydrogen side of the infrastructure needed. And from my experience, they've been very much targeted to follow a very similar model to the offshore wind of being intensive government support, with government then relying on market forces. What I was really interested to personally learn today from Tom's presentation in the morning was actually more about the impact of the voluntary market. So I suppose, how do you think SAF will fit within this mould? Will it be kind of government-led, or will it be a bit more market-focused?
Well, I think with the SAF mandate, the government has created the market. So the mandate obviously ramps up over the years between now and 2040, creating that market. But I'm also seeing that as a population, we are more open to sustainability and renewability. I always remember when I was working in oil and gas, I'd go home and my eldest daughter would turn her nose up at my career and say, "What are you doing, Dad?" And he was like, "Okay, the opportunity came along to go into renewability, so I moved across." But the younger generation are much more aware of these impacts that we have. So I think there's going to be a large voluntary market as well. You can see that the airlines offer you to offset your flights already. We can talk about whether those are true offsets or not, but that's there, and people take that up. And I think going forward, now the government set the market with the SAF mandate, I can only see it growing.
Excellent. That's really useful, really interesting thoughts. I suppose, Simon, do you have anything to add to that from your perspective, from obviously your involvement in another cluster as well?
Yeah, I mean, the UK has shown that the contract for difference business models work, and they've constantly evolved them for different sectors, and it appears that they're keen to make it work for SAF. So I don't doubt that it's going to work. They've got the experience, they've got the people, the setup to do that. I'm a little bit concerned about the administration of it and the bureaucracy and kind of the cost of that, but it's probably a small price to pay for getting these plants off the ground. Yeah, that's probably it.
Excellent. And I suppose staying with you, Simon, you were again. Tom did a great intro for this as well in the beginning this morning around actually the product, and as you mentioned, of your product going into the SAF market at the moment. So how does that really happen from a detail point of view? Are we seeing that? How's the blending co-processing work, and how do you anticipate this changing in the future where there is a higher proportion of SAF? So that would be great to get your insight on that.
Yeah, I mean, it's relatively low capital, to your earlier point, but it's quite complex. Different molecules to fossil crude oil you've got to deal with, and we're making things more and more complicated. With conversations around how do we make SAF from tire pyrolysis oil. It's not currently an ASTM-approved pathway, but we're processing it to make diesel and petrol. But that creates complications. We've effectively got to batch process it, so because we can't produce SAF at the same time as we're processing TPO. We've also got aspirations and plans to process recycled plastics, 2D plastics, to turn them back into a petchem feedstock that can be recycled back into plastics, but again, more complications. So, having standalone facilities to make SAF from this feedstock and this pathway, is clear and simple, but the costs are high versus co-processing and complications of multiple feedstocks. Okay, we've got lots of different units. So, at our refinery, we've got 4 cokers, 2 crackers, 2 crude units. So lots of routes that we can utilize to process different feedstocks. But it does get pretty complicated.
And so I saw you nodding your head there, Zainab, so I'm going to pick on you. But I suppose from your perspective, is that something that you see from either new build plants that people are looking to get licenses for, or kind of retrofitting plants in terms of, you talked before about the different technologies and the kind of a wide remit. So, I mean, I suppose, how does the back end, how does the co-processing part work for that and so for yourselves effectively?
I think, I fully agree with Simon, right? Co-processing, it can be challenging, depending on the amount you want to co-process. But we see a lot of engagement or a lot of interest from clients in Europe, in the US, revamping the existing hydroprocessing units to co-process, to produce SAF in the short term. I think that's an immediate solution, less capital intensive, but yes, it gets you there. I mean, this 10% by 2030. 2030 is 6 years away. It takes 6 years, 5 or 6 years to build a plant, right? So I think co-processing short term solves that problem.
Excellent. I'll try hopefully leave some time for questions for the floor. Just got a couple more on my notes. I suppose I'll probably start at least with Candice, or for this one, in terms of what do you, from your perspective, as from an EPC's perspective, what do you think what can be done for smaller independent suppliers to be able to join the supply chain? Because I suppose you have quite a wide view, so I'm quite interested to take your...
Okay, yeah, no, I'd be quite happy to mention about that. I think that there's quite a lot that can be done for these smaller suppliers. Certainly what has been introduced with the SAF clearinghouse is should be quite a big support for smaller fuel producers. Obviously, the traditionally larger fuel suppliers can afford to invest a lot to find technologies and help and assistance and assist with all the steps that need to be gone through, studies and permitting and investment finding and all this. But I think for the smaller ones, collaboration, I have to keep going back to, I think is key. So the SAF clearinghouse, where you can go and find information to help work you through that fuel readiness level pathway, I think it's excellent. But again, I keep harping on at collaboration and early engagement. So early engagement with potential investors, early engagement with the licensors, early engagement with the contractors to understand what's a helpful way of structuring that project, early engagement with permitting authorities. I know that that's something that sometimes can be a little bit of a stumbling block. Once you've got a project all ready to go and then trying to apply for permitting, that can be quite daunting. But early engagement with those different parties. And I would say as an engineering contractor, we work with clients of all different sizes. So, we look at potential projects for a fuel producer that's based within a metropolitan area that's looking at collecting the used cooking oil within their region and having a very small UCO to SAF processing plant. So it doesn't necessarily just have to be the Shells and the BPs and the Phillips 66s that can engage assistance and get that help. It's all about minimizing risk. And I think that happens through early engagement. And for fuel producers that are daunted by the thought of having to engage with investors and permitting agencies and licensors and all that sort, I would say engage the help of a consultant who have experience with dealing with all of those bodies and can assist you with it. But I think that early engagement is key. And for the projects that I see that move further along, they've been doing that from the get-go, so that there are fewer surprises, or at least if they come upon a roadblock, those bonds and those relationships are there that they can openly discuss and find ways around the problems and come up with solutions so that they get further along that process.
Excellent. And as I said, probably time for one or two questions just after my final one, really, where I will ask everyone to give a short one or two sentences, really, about this is a real textbook question, but I suppose about the UK SAF supply chain, what's the one thing you know now that you wish you'd known 5 or 10 years ago? So I suppose starting from Simon and working down.
Fairly straightforward and kind of builds off Candice's point. The amount of collaboration you need to do throughout the value chain is just incredible, and it's very rewarding. But 5 years ago, I didn't have a full appreciation for what level of collaboration needed to happen to get these first-of-the-kind technologies, pathways off the ground, projects developed, investments made, and steel in the ground. And I'm still learning that process. And maybe it's partly because Phillips 66 has historically tried to do everything ourselves. We've got a long history of developing our own projects. We converted our San Francisco refinery ourselves, but it's not the right way to go. You've got to work throughout the value chain with the technology provider, the startups, the airlines, the logistics companies, whatever. You've got to piece that together. And I think we heard it in this room yesterday from the investors, that's what they want to see to de-risk the projects, to get those investors on board.
Yeah, I agree, and I'd echo that. So I think, from my perspective, we don't have any regrets of the projects that we've been involved in, because everything that we've been involved in has been a learning experience to this point. I just wish that maybe 5-10 years ago that we could have had this engagement even sooner and engage with some of the folks that were perhaps trying to progress their technologies and progress their projects and maybe may have fallen by the wayside. Perhaps earlier engagement may have helped a few more of those come through. And even if they were smaller scale, we would have a lot more technologies, demo plant size, pilot plant size, that would be giving us learnings. So my thing is early engagement and getting started.
I have to say, I think everything that they said, plus as a business development person, the UK is leading the energy transition. And I love the fact that I now interact with a very diverse group of clients, right? So it's not just the refiners, traditional refiners, right? So interesting project developers from different backgrounds, power, EPC, you name it, right? So it's, and it just makes it super interesting. And again, going back, collaboration, I think that's the key.
Just to be, well, the same rather than different. When we started our journey all those years ago, we approached it as a competition. And I think the lesson we've learned is that you need to build partnerships and you need to build collaboration with your suppliers. It's not a master-slave relationship. We've got much better solutions, answers to problems by having that joint approach with our partners now. So we refer to all of our suppliers and vendors as partners.
Excellent. Very insightful answers there. I think as time goes, I'll just double check with Deborah. I think we've got time for maybe 1 or 2 questions, if that's... Yeah, so hand straight up. So we'll just pass the microphone over. We'll just be a second.
If you could just wait for the mic, because we need the stream, for the live stream. So.
Thank you very much. Chris Lewis, Director of the UK Staff Clearinghouse. Firstly, Candice, thank you very much for the unsolicited, excellent feedback. We're trying to do an important job. And to that, yes, I agree totally that whilst our main focus is on the technical suitability and negotiating with the industry in terms of evaluation, qualification and getting into service, we emphasise with some of these sort of newer entrants to the market that they need the cooperation of people who, you know, on the board there know what they're doing. They've been in the industry for years, and there is sometimes a little bit of reticence. It's like, I've got this brilliant idea and big oil's going to swallow me up, and it's like, no, it's not like that. So thank you for that, and I totally agree that we help them with that. We advise them on that as well. The question I've got is, if you've got a fully formulated product, so like the Fulcrum facility, which has got all its upgrading and everything, or you've got co-processing and it goes out into the pipeline and it's fully formulated, it's fully compatible with the system. My question, and I don't know who's best to answer it, is you talk about a hub and spoke model where, you know, intermediates are being passed around, or even like neat heifer SPK or FT SPK is being passed around the pipelines, which is not a drop-in. As we scale up at the moment, you could probably do it with tankers, but as you scale up, at some point, you've got to think about the infrastructure to get these, you know, the neat SPK or even the intermediates, which is more of a challenge around the system. What are the thoughts of the panel on that?
I mean, does anyone want to field that first? I suppose it was kind of, you were talking about Xolem's network before, Simon, so maybe that's a...
Yeah, I mean, it's a very good question, Chris. I've only recently thought about this, so I'm sure you've thought about it a lot more than I have. I wonder, Paul, have you thought about it from your project and how you integrate with other projects?
Sorry, Candice, could you... Oh, yeah, thank you.
Yeah, so when we were setting up the UK project, we looked at, obviously, in the initial project in the US produces FT liquids and then sends off a co-processor. So we looked at whether we could do something similar in the UK. But we decided at that time that we would go full upgrading rather than shipping FT products to a co-processing location. Simply because we didn't see that the infrastructure was necessarily there. It would involve road transportation to get it there. And we were trying to minimise our overall GHG. So we went down the route of on-site upgrading, then transportation of the final product by pipeline.
Yeah, so I think each plant is going to be different, and you're going to consider the benefits of trying to do what Fulcrum have done versus trucking components to another facility where to blend. And I think it comes down to trying to do it as simply as possible, but without creating more issues and costs down the line. So it's a combination between economics and still being able to supply that product into the market. But it's going to be a real issue that the industry is going to have to deal with. I think in the UK, because the UK is self-contained pretty much, although we are going to get lots of imports coming in, but those are going to be hopefully blended imports. I'm not sure we've really thought about it as an industry, and we do need to get our heads around it.
I will just add that we also have been considering a second site in the UK, and there have been some discussions as to whether we upgrade at that site or not, and whether we ship the FT liquids from that site to the first site and have a larger upgrader in that one area. But again, that's very specific to the Fulcrum product, and I think every product or every project is going to have to make those decisions on their own, based on what infrastructure they have around them, and based on how they will transport in that hub and spoke type environment.
Excellent, thanks. I think we've got time for one very quick question. Sorry, the lady at the back there. Sorry, you've got the sorry.
Hi, thanks. Sarah Wilkin from Fly Green Alliance. So today there was a great presentation by BA, and they mentioned that, and it was, obviously great work over a lot of years. They mentioned they're at 1% of their targets, and they need to get to 10% by 2030. As that's obviously by years. They need to make more than 1% a year, so that there obviously is some time factors involved. But apart from finding more time, what can be the catalysts now, and what can additionally help speed up meeting the targets? And do we need to mitigate for that? What's the catalyst, I guess? What can help in this situation? Are there blockers still? But what is the main catalyst to get that?
Okay, great. I don't know if anyone wants to lead with that. Is that something, Zainab, do you see that from a lot of your different clients around what can speed up their approach to FID, or I don't know if there's anything within there, or Candy?
Yeah, I mean, it's a very ambitious, it's a good target, right? 10% by 2030. And like I said, low carbon pathways, I think will get us there. E-fuels, yes, it's great to have, but I think there's some time to go for that. So I believe existing HEFA, co-processing, gasification-based routes, I think that will probably get us there.
Yeah, I'd like to add a little bit more on that. So, I mean, I think by the nature of it, luckily, even though we're talking about a 1% now and then a 10%, it's not a linear growth. So, clearly what we have are a bunch of plants that are going to come on stream. Hopefully 5 will come on stream, will be constructed in 2025. But then we will have discrete jumps as these SAF producers come on stream. So it's about enabling those projects that have sufficient capacity to hit FID and then to start construction at the right times. So I think a lot of it is, again, around minimizing risks. So like we kept talking about engagement and trying to engage with lots of stakeholders who have experience in getting through the various stages so that fuel producers and potential fuel producers can overcome their barriers. But also then I think, as I mentioned right at the beginning, and I try not to mention it too much, but coming back to money. So I think it's going to be about investment and ensuring that that initial investment that needs to be provided by fuel producers, that capital investment, is encouraged. The SAF certainty mechanism will help a bit to give investors confidence that they can apply it. But as we heard yesterday, just the sheer size of investment that's happening in the States helps a lot of those projects to get off the ground. And I think we need similar things here. We need as many different pathways to take off. We need many different fuel producers to be encouraged. So we need that funding to get started. And then once they come on in discrete blocks, I have confidence that we'll be able to make that. But we need that to get started.
Excellent. Well, thank you all. I'm afraid we've run out of time, but as Paul mentioned before, he does have a stand. He and his colleagues can answer any questions in the breaks. The rest of us will be around, so do catch us more. But I'd like to thank all of the panelists and Deborah for everything. So thank you all for attending.
You ready to take a seat and we can get started, please? Okay, good morning. Welcome to our panel on scaling power to liquids with nuclear energy. My name's Caroline Longman. I'll be chairing today. We've got some really great panellists who I'll introduce in a moment. But we're starting here from the point of the Energy Act 2023, which introduced nuclear-derived fuels to the RTFO for the first time, and that subsequently enabled nuclear to be included in the SAF mandate and enabled nuclear to be included as an energy source for the power to liquids route. So the aim of this session is to explore how nuclear can become a major solution in power to liquids, what we need to do to make this happen, and what the opportunity really is for nuclear-enabled power to liquids. So we're moving on very quickly. I want to introduce the first speaker, and that is Alan Simpson of Equilibrium. Thank you, Alan.
Good morning, everybody. And great to be able to talk today about this really important aspect of actually how we're going to scale up the decarbonisation of aviation overall. As Caroline said, nuclear-derived fuels are introduced into the Energy Act in 2023. And around 18 months ago, Equilibrium came into existence with a single purpose to widen the role of nuclear energy in decarbonisation and see it fulfil its full potential across the decarbonisation landscape. I just want to take a step back from aviation for a moment and reflect on the realities that surround the aviation sector in decarbonisation, because every sector is decarbonising. Domestic transport, shipping, heat, industry are all looking for energy to enable decarbonisation, and significant amounts of energy. If we look at the balance of electricity versus other energy sources in the energy system at the moment, we've got an awful lot of primary energy that needs to be replaced that does not currently come to us through electricity. And so this is a problem that I think the aviation sector will really need to grapple with when it comes to delivering SAF at scale, and particularly when delivering power to liquids at scale. By its very nature, it needs a lot of electricity, and combining the solutions that can deliver that electricity at scale with the PTL production solutions is going to be key to delivering the scalability with social acceptance. I think what we all want to avoid is the Daily Mail headline that talks about diverting electricity off the grid that's used to light people's homes to produce aviation fuel. That will be the end of scalability of the SAF sector when those sorts of headlines come through. So the SAF sector needs to be bringing through the energy sources to enable this. And we all know the scale of demand in the aviation sector for decarbonisation. There's 34 million flights a year to decarbonise. And they require an awful lot of energy. We calculated that to decarbonise with PTL across the board for SAF would require around 5 times the current global annual wind generation capacity for SAF production alone. So, Equilibrium, we believe the key to this solution is delivering nuclear-enabled SAF. We're developing a system, EQ Flight. It's an engineered system to take the energy from any nuclear reactor of any generation, and we believe that when coupled in particular to small modular reactors, we can generate circa 144 million litres of SAF per year from one facility. Importantly, the facility can enable the build of the new reactor, which enables the scale out of this production. And as Caroline said before, the policy supports this, and policy is an enabler for this. The UK government would say actually has a very enabling policy across nuclear and aviation, bringing them together. At the moment, there's a strong resurgence for nuclear in the UK, with the development of small modular reactors being driven by Great British Nuclear, and ongoing HMG engagement in how to scale up the sector. And we've got multiple developer organisations looking to deploy in the UK. And at the same time, the aviation policies are actively recognising the role that nuclear can play. The SAF mandate actively recognises nuclear as an energy source for PTL production. And when these things are combined, we believe that you can deliver PTL at lower cost, accounting for all aspects of fuel production, so minimising the environmental impact, delivering some of the lowest life cycle carbon emissions possible, using proven technologies and available to develop today. And ultimately, this is supported, we see, by a global aviation sector. And actually, I've been using this quote for a while now from Sir Tim Clark of Emirates about the need for modular nuclear to support PTL production. One of my wishes at the moment, if there's any airlines in the room, is it'd be great to have a British airline coming out with a statement like this to really recognise the importance of primary energy when we consider how we're going to scale up aviation decarbonisation. And with that, I'll hand back to Caroline.
Thank you very much, Anne. I'd like to welcome Tim Mays up, please, our second panellist. Tim is from the University of Bath. Thank you, Tim.
Good morning. My name's Tim Mays. I'm Professor of Chemical Engineering at the University of Bath. So I'm an academic engineer, if that's not a contradiction in terms. Really what I'm doing now, I'm a hydrogen man. So we're interested in hydrogen as a feedstock, not only to SAF, but to all kinds of other engineering systems and processes. But obviously today, the focus is on SAF. Just to give an indication of where I'm coming from, amongst the other projects I'm running a project called UK High-Res, which is all about prioritising and identifying research challenges that will accelerate the uptake of hydrogen in our rush to net zero 2050. So you can read this. The slides are, I'm happy to make the slides available to anyone who's interested. So we're interested in, it's a 5-year project funded by the Engineering and Physical Sciences Research Council, and the objective really is to, as I say, identify and prioritise research challenges related to hydrogen. So this is right across the value chain, making it, storing it, distributing it, using it. And we have around about £26 million of funding, partly from EPSRC and also leverage funding from industry. and I'll give a few details of that in a minute. And the key is that we work together with industrial partners and civic partners. There are civic partners involved in this as well as industrial partners. For example, local authorities in the southwest where I work. And we've done a consultation process over a year or so, and nuclear-enabled hydrogen became very clearly one of the priorities that we wanted to look at in the hub that we're running. So we have this level of activity. You can read that for yourself. So this is not an advert for UK high-res. It's an indication of how hydrogen may feed into the value chain for SAF. Now, we have eight research themes. On the left, it's the technical themes, and it's making it, storing it, and distributing it. And actually, we also have a theme related to alternative liquid fuels, including ammonia. And SAF may be considered as part of that mix. And we're viewing these technical themes through the lenses of sustainability, economic, social, and environmental, and also safety. I cannot overemphasize how much safety came up in our consultation process related to hydrogen. And so if you are a hydrogen man, and I am, or rather 10% of me is, it's a little technical joke there, the key is that we've got to do this safely, and if we don't, and there's any smell of casual approach to this, the policymakers and the public will pick up on it. And these are the companies and organisations that are invested in the hub, and you can see the range there. And the two I've picked out are the NNL, National Nuclear Labs, and also GKN Aerospace, both of whom have different angles on the work that we're doing. GKN are very interested in actually liquid hydrogen fuel aircraft. That's long-term, but also in SAF. And NNL clearly have an interest in the nuclear technology side of things. Excuse me. So we have significant investment from the government, from the public sector, significant investment from industry. And I actually am not a fan of the word green or blue or purple or yellow hydrogen. I much prefer the term low-carbon hydrogen. So we're interested in low-carbon hydrogen that can not only go into SAF, but all sorts of other areas. And you can think of hydrogen as sort of the Swiss Army knife of energy transition. This is just a cartoon, if you like, of how nuclear can enable hydrogen, either by heat or by electricity. And today I looked up the proportion of power produced in Great Britain by nuclear, and it's 15%. So 15% of electricity in this room is delivered by nuclear. And we shouldn't forget that baseload provision that keeps us going, but also the lack of intermittency. It chugs away nicely. Thank you very much. And intermittency can be a problem in delivering hydrogen, for example, from water electrolysis. And so nuclear, I think, is a key enabler for the future development of hydrogen, in particular to go to SAF, but to other technologies as well. So that's why we're interested across the patch. Thank you.
Tim, please come and join us on the panel. This way. Thank you. I'd like to welcome Mike Crawford from Rolls-Royce SMR as our third panelist. Thank you.
Hey everyone, good to be here. So yeah, I'm Mike Crawford from Rolls-Royce SMR, and I'm representing the nuclear technology provider right at the front end of the value chain. So I've got the job of explaining what is a small modular reactor. If I can get this to move on. Right. So address the elephant in the room is that this thing isn't actually that small. So it's closer in size to a football stadium than the shipping container you might envisage when you hear the term small modular reactor. But what it does get you is a huge amount of power output, enough to power a city of sort of 1 million people, around about the size of Leeds, which when we talk about the numbers here in the context of the energy transition is going to be really important. So the chart on the left here talks about the global electricity supply, of which you can see 39% is already decarbonised. And we talk about the challenge of getting that to 100% being really difficult, rightfully so, but we're off the starting block and we're tending in a good direction. When we zoom out to global energy, then that figure is 18%. And if you're one of the unlucky people sat in this room in the aerospace industry, then I'd imagine a metric like 39% decarbonised is something you would bite someone's hand off. So to deliver that energy, it's important to point out that nuclear is up there with wind, with solar, in terms of being clean and decarbonised. We'll come on to that in a minute, but the point is we need to pull on all the clean energy levers we've got if we're going to start hitting these astronomical energy requirements that we're seeing in the future. And so what is Rolls-Royce doing differently? Well, we're modularising the nuclear power plant, not just the reactor. By modularising across the entire power plant and treating it as a solution to a problem rather than just a design decision, we can ensure that this thing is made in a factory and it's delivered repeatably on time, and thus escaping the quagmire of cost and schedule overruns that has plagued the nuclear industry for the last couple of decades. And I'll say the civil nuclear industry, because during that time, in fact for the last 60 years, Rolls-Royce has been manufacturing quite small pressurised water reactors in a factory environment repeatedly and churning those out. Now, we've not made much of a fanfare about it because they go in a steel can and then they slip silently beneath the waves for 30 years, but it's possible and we've proven it. I won't linger on this slide because we're here to talk about SAF, but the point being nuclear reactors produce a lot of heat. That is their primary function. They're very good at it. The traditional model of a nuclear power plant, you put it in the middle of nowhere, and the only thing you can do with that heat is turn it into electricity and pump it into an amorphous national grid. The siting flexibility of SMRs that's unlocked by being smaller, by having a reduced water requirement, that lets you think differently and unlock some of these benefits that can only be achieved through co-location, so using that thermal energy to unlock a wider degree of use cases. And if you can use that to scalably and cost-effectively produce hydrogen, then that unlocks the whole wider tranche of decarbonisation that you see along the right. So that's key. And I mentioned siting flexibility, so I'll talk a little bit about what that means and where we're going to put these, just so you can sell your house if you live in one of those blue circles. Is that anyone here? I'm obviously joking, but the point of the graphic is to show the energy density of nuclear. And so if we were to supply the 2030 12 megatons of SAF that the UK will require, just by power to liquid, then that's the varying land usage requirements of nuclear compared to, say, solar or wind. Clearly, that won't be the only route for SAF production, but SAF's not the only challenge. We've got to decarbonise the energy system, we've got to decarbonise industry, shipping, we've got the rise of AI and the huge power-hungry data centres that we need to supply. So again, we need to pull on all of those clean energy levers if we're going to make that happen. As a nuclear technology, we are rather agnostic of what that fuel mix is. So there's lots of debate about hydrogen, electric flight, things like that. Ultimately, whether you are using batteries for short scale, hydrogen for medium, or good old hydrocarbons to achieve long distance, you still need energy, and nuclear can provide that. Even through biogenic SAF routes, they still need lots of heat in all those chemical processes. When we talk about the scale that we're talking about here, getting off the 1% into the 40-50% of total fuel demand. And then nuclear can provide all that energy sustainably. So this is the carbon intensities of various pathways with the UK government's sort of data quoted in the SAF mandate. And as you can see, nuclear is the most effective way of decarbonising. And so we have to ask ourselves, what is the problem that we're trying to solve? That's it, I think. I'll leave it there. I'm going to, for brevity.
Thank you. Thank you, Mike. I'd like to welcome Robert Alford from NNL. Thanks, Robert.
Morning, everyone. Afternoon, sorry. National Nuclear Lab is the UK's government-owned lab for nuclear fission, so taking uranium and splitting it, working across all levels of waste management, new fuel. What can nuclear do beyond electricity, which is what I'm going to cover more today. So picking up on that last presentation, at the moment we take a nuclear reactor and we use that heat to turn the turbine electrons into the grid. That actually is a relatively inefficient use of that primary heat energy which comes out of that reactor. When you split your uranium, you get your heat. And this is what this is showing is all the opportunities of how we can use that heat to decarbonise all those industrial, all those heating demands, and all those transport demands, which is obviously what we're discussing here today. So, as an example to pick up on for this audience, I'm showing there us tapping off that heat to therefore split your water to make your hydrogen. I'll come on to methods for that in a minute. The endothermic reaction there. Same with carbon capture, how you are capturing that carbon, again, energy intensive, to then combine Fischer-Tropsch or Haber-Bosch into your liquid carbon fuels or ammonia. We've taken this to then make a 20,000 piece Lego model to help engage people with this. That wiring diagram is great when talking to some people. I saw some of you photographing it. But when I'm talking to school children and other audiences, then having a Lego model definitely goes a long way. And for this audience, I've got a little airport on it. And I hope for the aviation sector in the room, my windsock is pointing the right way with the plane taking off. If it's not, please come and tell me afterwards, and I will adjust the angle of my windsock compared to my plane. But anyway, slight joke there. In summary, what I'm saying is, it's the education bit around what nuclear can do and the harnessing that energy and that heat. And as you can see, we've got our wind, our solar, etc., because it isn't a competition. We need every single form of energy generation, low carbon, that we can. Right, coming on to where we are as a UK at the moment. The government released in January this year the Civil Nuclear Roadmap 2050, and that set out this ambition for 3 to 7 gigawatt of new nuclear every 5 years, so every parliamentary period type thing, and then up to 24 gig by 2050. Where are we at the moment? At the moment, we have just under 6 gig on the grid. We're building Hinkley over in the southwest. That's 2 units that come up to 3.2. And we've just got approval, you'll see in the news yesterday, progressing, was it earlier this week at least, about Sizewell, the 3.2 there, and potentially more in the mix as well. You can see at 24 gigawatt, compared to what we've got now, we have committed to quite an ambition here. Alan mentioned Great British Nuclear. Great British Nuclear was set up by government early this year as that body to help us realise and obtain these ambitions. So to deliver the SMRs that we've heard about, we need sites. And GBN, Great British Nuclear, have obtained the 2 sites listed there to help enable new nuclear and get these nuclear power stations rolled out. And we don't have all these challenges that we've seen over the last decade and all the frustrations that the sector has seen. We now have GBN to help streamline this process. Just to cover reactors, types of reactors, to give you an update and fits in with the small modular reactor bit. So at the moment, we have 8 what are called advanced gas-cooled reactors on the grid, all operated by EDF, and they are coming offline. They're getting towards the end of their life. They're actually beyond initial design life. Then we have Sizewell B, which is our 1 light water reactor on the grid, PWR on the grid at the moment. Hinkley Point C, Sizewell will be the same. You can then scale that down, as we've heard, for the SMR designs. So they tend to be, or are, smaller in actual output, and obviously modular build, as we've heard. And then the next generation are these high-temperature gas reactors. And we're working with JEA, Japan, on this. This is developing the next generation, Gen 4 reactors, operated at a higher temperature and a new accident-tolerant type of fuel within. And that is something that we are developing up towards the 2030s. So just to summarize a bit on where we are with nuclear, we've covered some of this before. It is amongst the lowest carbon emitter of all energy technologies across the full life cycle, including all the mining, the concrete for the reactor, etc. We are equal with solar and wind. It's among the safest. People think nuclear is unsafe. People worry when they got an airline. Airline travel, as you all know, is safer than car travel. So why are more people scared of airline travel than getting in a car? It's the same with nuclear. Nuclear is safe. And if we kept telling you we're safe, you might actually believe that we're safe. Most energy dense, the least area. We've seen the graphic in the previous speaker as well. It is a very energy dense form of energy. And there I've got on the right the 3 different forms of large scale, small modular reactor, advanced modular reactor, and the temperatures they operate at as well. To quickly cover types of hydrogen generation. So wind, solar, low temperature electrolysis, so effectively coupling up your electricity to then split your cold water effectively. Nuclear's USP to that is the high capacity, the constant output that we've heard from Tim before. Next up, you have your high temperature electrolysis. So this is where you're using that heat. As I mentioned, the primary product from your nuclear reactor is the heat. So you're harnessing that. And we're doing some work at the moment with EDF, Bay Hydrogen Hub, up at Heysham near Lancaster, to tap off the steam and electricity from Heysham to then generate hydrogen. And moving on, future generation of technology is thermochemical. It's lower technology readiness level, but this is a method of using potentially that extra heat that the AMR offers. This is just a quick graphic to show what I mentioned there against the low temperature versus tapping off that heat. The same nuclear reactor, the 1,000 megajoules coming out of it, if you put it through the desk electricity, 1.84 kilograms of hydrogen at the other end. If you use some of that effectively waste heat, you can see there the extra efficiency you get. And that's what Bay Hydrogen Hub up in Lancaster is going to demonstrate. Oh dear, the formatting's gone a bit to pot. We've just released last week a report on technical economic analysis of heat-assisted hydrogen production. What does this show? The first bullet point shows that, we can ignore that one. That first bullet point just says that it's released last week. The first real bullet point says that high-temperature steam electrolysis has efficiencies through using that nuclear heat, as I mentioned. And we've also compiled in this that HTSE, high-temperature steam electrolysis, is the way forward with our current reactors. And then moving on to the medium term, so with SMRs, again, high-temperature electrolysis is the way forward with that. Going forward, as the AMRs develop through the 30s and 2040s, potentially thermochemical will be a method to go forward. But at the moment, our recommendations and what's in this paper, if you scan the QR code, is high-temperature steam electrolysis is the route forward, coupling to a nuclear power station. And finally, oh dear, invisible text. That's really not good. We've released a report, Decarbon Regional Growth. It summarizes a lot of what we've heard today, all about the energy demands, the challenges we have, and it has within it an aviation case study. This explains the challenge we have at the moment with decarbonising electricity. Great, that's only 18%. Over 80% is, as I mentioned, the industry, the heat, the transportation. And this goes into a lot about what nuclear can do. We've got into some public polling, some engagement. If you can't scan the QR code, I've got postcards with it on as well. And I look forward to chatting more with you during the panel. Thank you very much.
Thank you, Robert. Please come and join us and we'll have a chat. Take a seat. Thank you very much, and thank you to all the panellists for their presentation. We're going to just ask a few questions between us now, and then we'll open it up to the audience. I'm going to work out how to use this microphone and hand it over to Mike, because I'm going to give Mike the first question. So it was really interesting to hear your presentation on Rolls-Royce and the SMR design, part of this new generation of nuclear reactors, and you talked about the modular design and how that's going to make it well suited to construct many units across the country and scale deployment. So we're here to talk about nuclear SAF production. How do you think that modular design lends itself to SAF production from nuclear?
Yeah, good question. So the way we've approached that modularization is to solve those challenges of deliverability and to be taken credibly as an energy solution. And I think when we start talking about being able to deliver at scale, we need that credibility. We need to be shown to deliver so that when we get on to more advanced nuclear projects such as cogeneration, we can hold credibility in the investor community and get the finance to make them happen. So in terms of the actual integration between these, it's very little. And so the Rolls-Royce SMR is around 2,000 modules, and you only need to change 2 of those to go from an electricity producing plant into a SAF plant integrated beast. And so it does allow you to do that, but it's all about just that delivery certainty, giving certainty to projects to make bigger projects happen.
Brilliant, thank you. It's all about the scale, isn't it? And I think it sounds like modular construction enables easier access to scalability, and that's when we're talking about nuclear power to liquids, we're talking about scale, and I think that's where one of the value adds of nuclear as an energy source for SAF production. So on the value add of nuclear energy, I just want to hand over and ask a question to Alan over here. You've got your own microphone. I don't know how you switch it on, but hopefully you've worked it out. So in your presentation, you talked about how important energy availability is to drive PTL production and the importance of nuclear. So could you just elaborate a bit more around what are the constraints on PTL, on that PTL route in terms of energy availability, and how can nuclear address those constraints?
Yeah, thank you very much for that question, Caroline. I think one of the things we've looked a lot at in terms of PTL production is how we optimise PTL production to use nuclear energy. And one of the things we see in a number of projects is the constraints of variable energy in making those projects efficient and being able to run the chemical reactors all the time. The great thing about nuclear reactors is they run constantly for 18 months at a time. And so importantly, when we think about the temporal correlation requirements in the SAF mandate, nuclear naturally meets those requirements. It can run that plant 24 hours a day, 7 days a week for 12 to 18 months at a time, delivering low carbon energy, as Mike pointed out, that meets the requirements of the SAF mandate. But also because of the ability with small modular reactors to look at building off-grid solutions, we can also overcome some of the constraints around meeting additionality requirements on the grid, because we're building a new energy source that is not touching the electricity grid. And so therefore it naturally overcomes some of the additionality constraints for the more energy on the grid. And that's before we consider how we can use the heat that Robert talked about to, again, optimize a number of the processes in the system and gain more efficiency out of the whole system. So our work to date has shown that being able to use that consistent energy, being able to use the heat, and optimizing our whole system around that can deliver some efficiency gains that are embedded efficiency gains that cannot be met without the external source of consistent heat and electricity.
Additionality is quite an important component, isn't it, when you sort of mention that, but it might be worth kind of elaborating on that.
It absolutely is, because if we consider the number of demanders on the national grid at the moment, one of the kind of key requirements that government puts around putting additional draw onto the grid is that if you are going to divert low carbon electricity on the grid for other uses, then you need to replace that low carbon electricity on the grid with more low carbon electricity at the same time. And so actually it puts a real constraint on the ability to use grid connected systems for low carbon electricity, and it's what drives the high costs associated with low carbon grid electricity at the moment in the UK. And this is all going to be reflected over the next decade at least, with the primary focus in the UK on decarbonisation of the electricity grid as one of the key priorities.
Thank you, Alan. I'm going to move over to Robert, if that's okay. I love the Lego model, by the way. Thank you for that. It was really interesting to hear how, and a really good overview, if I might say, on the different types of reactors being developed and how they can be used, and the kind of relevant merits of each of those reactors. And we talked about safety, and you talked about safety, and one of the areas of challenge that we get as a sector is waste. And so I wanted to ask your view and your on in terms of what about the end state. So nuclear can deliver SAF. We're talking about the merits, the opportunities for nuclear, but let's address the challenge of nuclear waste. It's often misunderstood. Is there a problem? Does the sector need to do anything to address it? And yes, it would be really good to have your view.
Thank you, Caroline. So yes, waste is something that we often get quizzed on. And I think we need to remember where the sector's come from. In the 40s and 50s, we were pioneering nuclear for the world. We weren't too worried about the waste management challenge back then. And if you think about Sellafield and the legacy we've got there, it is significant. I'm not going to underestimate that at all. And we are having to invest a lot in that. But that is a sector which is quite different to where we are today. And I think if we look at what we've got then, and we didn't do waste hierarchy in the same way then, we just put everything in silos. We'll deal with it next generation. And I think lots of sectors do the same. Lots of sectors pioneer the actual product and then start worrying about the waste. And we're seeing it to some extent with renewables, with solar and wind, and now how do we do the recycling of the solar panels? How do we manage our wind turbine blades? We also have something now called the Nuclear Liabilities Fund. So whenever you build a new nuclear reactor, and the cost of it includes the full life cycle cost, and that includes disposal of the waste. And this isn't vast, vast quantities. People think we generate large quantities of waste because they think of Sellafield. That's the historic part of the sector. Nowadays, we do embrace the waste hierarchy, and you can see various numbers out there. A Coke can of nuclear waste per person is kind of the ideas of what people are sharing. And the total, we talked about football stadiums before, the total waste volume of all our current nuclear waste, and that predicted to arise, is the same as Wembley Stadium in volume. That might sound quite large, but we can capture that. The difference is, with fossil fuels and other forms, you are admitting that. We have the benefit, we can capture all our waste, and we can then invest the money, look at how we do manage that. And there is billions of pounds across the globe being invested in our various repositories for that safe, long-term, multiple centuries of safe disposal of this material. So yes, it is a challenge, Caroline, but I think we need to be aware that we need to think, yes, we've got a history with the legacy, but we are behaving very, very differently as a sector now with our new reactors and the waste that's generated.
Thank you. And I think all forms of energy generation create waste.
They do.
And we have to, as a sector, work really hard to address perceptions and make sure that we communicate. And I know you do a lot of the outreach and the communication to make sure that, you know, it is well understood how we manage waste, how we're going to plan to manage the waste in the future. Okay, thank you. Can I pinch your microphone because I'm going to move over to Tim. So I'd be really interested in your perspective because I know that you've been working on the development of hydrogen and SAF for quite a few years. And in terms of the role of nuclear in clean technologies going forward and SAF, what's your view?
Thank you, Caroline. I think new nuclear and hydrogen are a marriage made in heaven, actually, I think. New nuclear comes with heat and with power. And I think both of those in combination can be used very efficiently and effectively to make hydrogen. So I'm a hydrogen man, so I can see hydrogen feeding into SAF together with CO2. And that's, if I may say, a bridging technology. I hate to say this, but I see SAF as a bridging technology to run out the current fleet of aviation running into likely liquid hydrogen fueled aircraft. That's my prediction, although I'll be 6 foot under when that happens. And so I think that nuclear-enabled hydrogen is a really rich and important area. We can deliver the hydrogen to make SAF, and we can also then deliver hydrogen downstream to power aircraft directly, without any carbon. And some of the points that have already been made by experts more knowledgeable about these systems than I am, you have this interesting combination of heat and power from a nuclear reactor. And both of those can lead to very effective hydrogen production. And I would say that SAF is a very useful chemical output from hydrogen processing. But it's not the only one. You can make low carbon ammonia. You can use the hydrogen in the transport sector. You can use it in heating. So it's flexibility, I think, of hydrogen, and I'm sort of advocating the hydrogen side of things. We have a nuclear advocate, and I think the two go hand in hand. I really do, and I'm a big fan of nuclear. Yes, there are issues to do with how you manage the waste, but new nuclear is much more savvy compared to old nuclear, the AGRs, and even before that, the Magnox systems. So I think that we've learned some lessons, and as a process engineer, I see some real technological and thermodynamic, if I may put it that way, advantages of using new nuclear heat and power to generate hydrogen that can go into SAF in the short term, can go into liquid hydrogen in the long term, and into other sectors as well. How about that?
Thank you very much, Tim. Can I just pick up on something you said? When you talked about SAF being the potentially a bridging technology, and ultimately the future would be hydrogen, liquid hydrogen planes. But you'd be 6 foot under. But like, in terms of the timescales, is this you know, the ultimate future of low carbon aviation? And are we talking 50 years or 100 years down the line? How long is that bridge?
I hesitate to give any numbers to this when we have Boeing Airbus and other in the room with us, I think. My own personal, this is a personal view. SAF definitely is, to my mind, a bridging technology to decarbonise kerosene so far as you can, but ultimately you're still pumping CO2 into the atmosphere, whether you like it or whether you don't. Now, you might say you're recycling it, and it's in a virtuous loop, but I'm not so sure about the mass balance of that, to be honest. But nevertheless, there is a fleet of aviation that needs to decarbonise, and either you don't fly or you try and have decarbonised fuel. And SAF clearly is that technology to be allowed to be able to do that. Now, the current fleets for aviation have probably got 30 to 40 years of life in them. And they're expensive machines to keep going, and you want to keep them going as long as possible. Indeed, like a nuclear reactor, you want to keep it going as long as you possibly can. But ultimately, I see that you want to decarbonise completely. In other words, don't have any carbon in your fuel at all. But this is long term, and my guess, if I was put on the spot, Caroline, thank
Sorry.
you, is 20, 40, 50.
Okay.
For a hydrogen aircraft, but they have to redesign the aircraft to run on liquid hydrogen. So you have a machine that already runs very nicely, thank you, on kerosene or a substitute.
Wonderful. Thank you very much. Sorry to put you on the spot.
No problem.
So I think it would be a good time to open up the questions to the room. So I don't know if Deborah's a speaker there, a microphone there. If anyone's got any questions for any member of the panel, please just pop your hand up and I'll try and spot you. John, over there. Raised. John's over here. Thank you.
Is on. That surprised me. John Woodburn, Public Affairs Manager at the Nuclear Industry Association. We're the trade association for the civil nuclear sector. My question to the panel is, what are the, in your view, the critical strategic enablers that government can put in place to enable power-to-liquid SAF in the next 5-10 years? So what do you need to see by government, and what do you see as well from other countries around the world? Because it's not just a UK effort, it's a global effort. So it'd be good to hear your views on that. Thank you.
Thanks, John. I'll invite all the panel to answer, but it's okay. I'll start with Alan, if that's okay.
Yeah, absolutely, and thank you for that question, John. I think one of the things that we see most commonly is it's about time, and it's about the recognition that bringing nuclear reactors online, new nuclear build online, is going to take time. So what we would really be looking for and encourage is that in developing all the policies, to consider how long it's going to take to bring the new energy sources online, in particular nuclear, that can deliver the SAF at scale, and consider how much lead-in time is needed in, say, revenue support models between the support model being agreed and the plant coming online, but also in how long that plant needs to produce to earn back the capital costs associated with it. Small modular reactors are still going to be expensive, capital-intensive infrastructure projects that last a long time. And so we need a suitably long enough payback time on the product being produced to make it financially viable. We heard in the keynote by Tom Byrne earlier about the 14-year takeoff agreement for SAF to enable an e-fuels route. We can absolutely see that takeoff agreements as long, if not longer than that, will be required to enable nuclear. Other than that, I would say that I think the UK has really strong enabling policy in this area, and it's about coherence and connectivity between some of the policy on the energy production side and supporting new nuclear, and SAF as the off-taker of that energy and the feeding through to the airlines.
Thank you, Alan. I'm going to invite the other members of the panel to answer the question as well. Tim?
Yes, I'm going to get all philosophical, as is my want as an academic. Unfortunately, I wasn't able to make the meeting yesterday because of the GWR strike, thank you. And so I've only joined the meeting today, and I haven't heard much word about catastrophic climate change. The ultimate motivation for my work is to mitigate an existential crisis for humankind. And the motivation to solve that problem, we can employ technology to help us do that. Nuclear is the subject of this session, SAF on the broader landscape of this conference. And I think both will have an important role to play in decarbonising our economy. But we can't forget why we're trying to decarbonise our economy. It's to avoid emitting CO2 into the atmosphere, leading to catastrophic existential climate change. And some of you may have read today of the predictions of experts, IPCC experts and so on, about what they think about the temperature excess will be. And many more think it's going to be greater than 2 degrees. Not 1.5, but 2. Or maybe even 2.5, 3 degrees by the end of the century. And I think we shouldn't forget that overriding motivation will ultimately and should ultimately trickle down into regional, national policies. And I think that we have now, with the incentive for new nuclear, for hydrogen, really important decision points we can make. And I hope that future governments will take this on board. But I'm afraid I'm waffling a little bit now because I get quite emotional about the fact that the reason we're doing this is to decarbonise the world and avoid a catastrophic existential crisis for our civilization. Sounds very melodramatic, but that's where I think we are.
Thank you. And I think it's right to highlight this is a global problem. So the opportunity here for nuclear-derived SAF could be a global solution. And there's an opportunity for the UK to bring forward the right technologies and the right collaborations to lead the world in that respect. Thank you. I'm just going to invite the last two panellists to answer John's question, and I'll move forward to
Just quickly wanted to mention the government's Great British Nuclear Competition, which the thing that they could do is conclude that as quickly as possible so they can start making some firm commitments and make SMRs real. Then the community will have the confidence to be able to go forward and put money and investment behind other projects like nuclear drive stuff.
Thanks, Mike.
Yeah. Coherent, consistent, all of this. For me, it's around the engagement piece. So I spent some time seconded into DESNZ or BEIS at the time, and you've got Department for Energy, or BEIS at the time, DESNZ now, Department for Transport. For me, it's joining up the dots, and it's the consistent messaging, it's the ensuring it is enabling across the various places, and we're not talking in silos. That's my succinct answer.
Thank you, Robert. I don't need that, do I? Over there, please. Here, please. Sorry, Sarah. I think it's Sarah. Yeah, behind. Thank you. Alistair, I'll come to you after.
Yeah, my name is Sarah Wilkin from Fly Green Alliance. So, yeah, as you were mentioning before, perception is definitely part of things. And we did put nuclear into our trends last year, so we are contributing. And as you know, we're discussing things as well. So I also went to a Dutch fusion day, and there was actually 200 people at a nuclear fusion event. So obviously that is another topic. We're talking about fission here. But actually we're here with Innovate UK today, but what about from an EU perspective? And actually I spoke to Hazel from Department of Transport, and fusion is in a net zero plan, so the UK is enabling nuclear to be basically part of roadmap. So that's all strategically underway, she mentioned. So what about the actual a more global perspective? How can actually learning or collaborating with other either EU member states, obviously, so the UK is now back in Horizon Europe, which is brilliant. It means there's going to be greater collaboration at an academic level. Do you have thoughts about whether it's EU member states or globally, what kind of can that do to be a catalyzer or support in general?
Thank you, Sarah. I think I'm going to hand over to Tim to pick up on the academic angle that you talked about.
First of all, I think the collaboration opportunities for Horizon Europe are immense, but there's also a significant energy barrier to overcome that we need to break from the break in European funding we've had up until now. So in other words, lots of consortia and other have actually got together already, and the UK's sort of running to try and keep up. So I think there is an opportunity, but we can't. I wouldn't say that it's an easy one. We need to fight hard to get back into the game. In terms of fusion, it's interesting because the UK is actually powering ahead, no pun, on fusion with the STEP system. Although it's pilot scale or further than pilot, but there is, I think, the joke that that fusion is 30 years away at any point of time is getting a bit worn out now. And the sense is that from talking to experts that fusion is nearer than we've ever had it before. And while fission will still remain an important component, I think, of baseload, I think fusion will certainly come along in its own right for power and heating, but also delivering electricity from an electrified world via hydrogen, perhaps. But I think the Horizon Europe option is an important one, but I'm a bit worried that we think we can just run straight into the Horizon Europe without having to do a bit of work beforehand.
Thank you, Tim. I'm going to just pass the mic to Robert.
Yeah, thank you for the question. Collaboration, totally agree. I think air knows no boundaries. We can go net zero, but the rest of the world needs to as well to stop this problem. As National Nuclear Lab, we have formed a collaboration centre called Global National Labs Integrated Energy Systems, and it is on the exact topic of how we all work together. I've just got back from South Korea myself. I've seen how they've continued building for 50 years. They've not stopped. We made a mistake. We stopped. And they, therefore, have seen costs come down. They've seen how to enable nuclear more. And therefore, for me, collaboration, such as our GNLIES Collaboration Centre, is the key way to enable this. Idaho National Lab over in America, they're doing testing with Fuel Energy and Bloom Energy on electrolyzers. They've got their Marvel reactor. They're doing micro-reactor type technology. We're working with them on this because we want to solve this challenge as a globe, not as the UK.
Thanks, Robert. Alan, do you want to?
Yeah, absolutely. A couple of thoughts on this. I think my starting point for this is the UK is a great place to deploy nuclear-enabled SAF. But at the same time, across Europe, you've got lots of countries actively developing and delivering new nuclear projects, particularly for electricity production. So you've got a build-up of the skills base across Europe that can be reflected and support the build-out of nuclear in the UK for SAF, as well as then the knowledge and skills for SAF production from nuclear being shared across Europe as a result of that. And that also plays on to the fusion point. I think it's important to remember we talk sometimes about nuclear fusion, nuclear fission. From a SAF production perspective, it's the same technology. Both nuclear fusion and nuclear fission produce large amounts of heat that can be converted into electricity. So if we can commercialise SAF production systems that are optimised for nuclear, when fusion comes along, it can plug and play into those production systems as a solution. And so there's a great amount of collaboration in all the different elements of the system there, where different countries are progressing ahead of others to be able to share that knowledge and experience.
Okay, thank you, Alan. I want to go to, I think, Alistair, you had your hand up, and then I'll go the other two. We've still got a little time left, so we can answer everybody's question.
Thank you, everyone. It's Alistair from Carbon Neutral Fuels, and there were some really interesting presentations there. What we've seen is that nuclear has traditionally been run by governments and predominantly for domestic electricity production. We've kind of run the numbers, and Alan kind of arrived at a similar conclusion that potentially PTL SAF is a bigger opportunity than domestic electricity production. Does the panel see a future where you potentially have privately funded small modular reactors powering PTL? And what do governments need to do to kind of enable that?
Okay, I'll pass over to Mike if that's okay.
So yeah, easy answer is absolutely. We do see that as a technology vendor. That the challenge is getting over that hurdle of making these real and the first of a kind, keeping that as simple as possible in that investment case, making it workable. But once you get beyond that and this becomes routine and it becomes a productionized product, then yeah, it really opens the floodgates. And so yeah, as you quite rightly pointed out, that sort of hydrogen SAF use case could be far bigger than the traditional electricity to grid. So yeah, we do see that.
It's incredibly interesting, isn't it? Alan?
I echo Mike's comments there. Yes, absolutely. Once we've overcome those first barriers, the first systems, these can be privately led, privately funded projects. I think it's important to note, though, that government will always be involved with nuclear, particularly for the fact that across the world, governments that have nuclear operating in their countries ensure the ultimate nuclear risk. This is well demonstrated in America, which has had a significant amount of privately led nuclear deployment. The American government still ensures the ultimate nuclear risk, and so government is always going to need to be engaged, if not the funder.
Thank you. Thanks, Alan. We had another couple of questions just over there at the back. Please. Sorry, I don't know your name. Thanks, Ray.
Good day, everyone. I'm Inke from Mongolia, and Mongolia is a small country sandwiched between Russia and China. We are almost 100% dependent on Russian aviation jet fuel. And today and yesterday, I received a lot of information how to go the SAF and the future of the SAF situation. And of course, the Mongolia wanted to become more independent from the supply from Russia on aviation, jet fuel. And because Mongolia is very rich in minerals, especially uranium, and Honorable David Cameron visited Mongolia last week and tried to expand business relationship with Mongolia, especially on the rare earth materials. And my question is whether the UK or private project handlers interested to expand their business to develop in Mongolia, because Mongolia is only 3.5 million population. Land is 3-4 times bigger than France territory, and we have a lot of uranium. And just wondering how much would be smallest reactor to establish or build in Mongolia. Thank you.
That's absolutely fascinating question. I'm going to give Mike the privilege of answering first.
Thanks. Yeah, but believe it or not, you know, this is not the first inquiry for nuclear that we've had from Mongolia, and I believe the UK government gets asked quite a lot. The challenge that Mongolia have is to be an owner of nuclear technology. There are a number of milestones, so the IAEA, International Atomic Energy Agency milestones that have to be achieved to sort of qualify you as a responsible owner. As a country, and a number of those things include a long-term waste disposal plan, having a regulator that's qualified and set up and competent, and that takes time. And by time, I mean decades. And so that's the challenge facing Mongolia versus some of the markets that we see as the quickest first wave to deploy, like the UK, where we can get going in theory tomorrow once we have that signal. So. Absolutely, it could be potential in the future, but it's got its journey to go on, and that needs commitment from the government because it's a multi-election cycle journey that it needs to go on.
Thanks, Mike. Tim, do you want to say a quick word?
Yeah, a general point. First of all, it's great to have someone from Mongolia here. I hope you're enjoying your visit to the UK, if that's where you're, how you're here today. It's interesting, the geopolitical dynamics are changing because of the resource requirements for different technologies are changing. All of a sudden, lithium's very expensive, very sexy, uranium, as the new nuclear starts to develop. And I think that countries that formerly may have relied almost exclusively on petrochemicals, in your case from Russia, and maybe from China as well, may be in a stronger position. And I think the UK should do its ODA, its overseas development support for these technologies, because you may actually be in quite a strong position, not only for your own internal energy markets, but also in terms of supplying a global demand. So I wish you all the very best on that, because I think the geopolitical changes that are happening in the world now are very, very interesting, away from fossil.
That's brilliant. Thanks, Tim. Robert?
I was just going to add some bits in terms of that export market piece. I was at COP26, as some of the other people here in the room were as well, and we had lots of people coming up to us from some of the developing countries saying, how can you help us? And I do see that, as I mentioned on this global challenge we face, we are going to have to support the developing world a lot more. one part we're looking into a bit at the moment, not as applicable for yourselves, is floating nuclear. The idea of, can you float the nuclear reactor into a port, you plug it in, and then that nuclear reactor goes back off to its original country for the waste management, the processing, etc. There's a lot about insurance, regulation, etc. on this. It can't happen tomorrow type thing, but the cogs are starting to move, I think is the key thing to say, in that we are aware this is a challenge where we have to support our neighbours a lot more.
Thank you, Robert. We've still got time for one or two more from the audience. There's two over here. This lady had a hand up before, and then we'll go over. Oh, gosh. Okay. Need to run, Ray.
Get my steps in. Sorry, who was it?
Thank you.
Hi, I'm Candice Carrington from Petrofac. So at Petrofac, we've looked at various routes to SAF production, so whether it's heifer, Fisher troughs, etc. And power to liquids is very interesting to us as well. One of the things that's quite clear to me, though, is the cost of electricity that goes into making the SAF via the power to the eSAF or the power to liquids route. I was interested to know if you have thoughts on it. What do you think utilizing nuclear could do to the levelized cost of hydrogen, or perhaps, cost of electricity, but particularly levelized cost of hydrogen, if you can comment on that?
Thank you. I think all of our panellists will probably have a view on this. It's a question I'm surprised we haven't had already. So yes, thank you. I'm going to pass over to Alan.
The short answer to that from my perspective is that it can drive down that cost. There's a couple of factors that feed into this. One, the fact that we've got that consistent electrical generation, which means you're utilising that capital-intensive asset all of the time. Also, the fact that we can get some of the additional efficiency from heat really helps. But also, the new generation of nuclear reactors coming through in the small modular reactors, that modularity and that factory build really enables a long-term driving down of the cost. And we see that there's an opportunity, even with first-of-a-kind technologies, to be cost competitive before we take in all those learnings that can be achieved across the chain to drive down the total cost. There's been some modelling that I've been involved with that has demonstrated that nuclear-enabled hydrogen and therefore feeding into anything that makes use of hydrogen, is lower cost than renewables-enabled hydrogen.
Thanks, Alan. Mike?
Yeah, well, I agree with all of that, and I'd add we've just completed a study in the Netherlands with a number of industrial players, including Topso and McDermott, that demonstrated nuclear-derived hydrogen, which obviously is a big factor in the final SAF cost, would be half of the price of using renewables-based equivalent. And if you're willing to operate flexibly, i.e. when the energy prices are high, you stop making hydrogen, then you could half that cost again. So a quarter of the cost, which is a huge result.
Wow. Goodness me. Thank you. That's interesting.
Yeah, I think similar to the previous two, we've done research ourselves. We've published some stuff on our website about this. And yes, levelized cost of hydrogen can come down below comparable with renewables. I think a key thing, electricity price-wise, is we often think about it coming out of the grid. The grid is very expensive. If we can do behind the meter, the price of it does come down a lot. And as we talk about the new nuclear going forward, not necessarily being primarily electricity generation, it's the other way it can support transportation industry. We may end up with a lot cheaper electricity coming out of those reactors because we're not paying the grid price, we're behind the meter.
Thanks, Robert. Tim, do you want to make a quick comment?
Yes, in terms of spot price or levelized cost, there's no doubt that hydrogen costs can go down from nuclear, as Alan's mentioned. But I would also say that we often forget, and I'll go back to this philosophical point I made about climate change. The Stern Review in 2006 suggested that there could be a 20% hit on GDPs if we don't do anything about climate change. And so while the spot price of whether it's heat or power is very important, and I understand that, or oil or gas, we also all need to think about the embedded cost of not doing anything. And I can't remember seeing a business case for anything that necessarily builds that in. The Stern Review made it very clear. If we don't do anything, the GDP could take a massive hit, both with trying to deal with the consequences and then trying to mitigate. So forgive me for getting philosophical. in the room full of experts and engineers working at the sort of hard face of the economy, we shouldn't forget that there are overriding costs that we sometimes forget about.
Thanks, Tim. Are we okay for a couple more questions? I think we've got Pete over here, and then are we okay, Deborah? Are we okay to take a few more questions? I know we're over slightly. Okay, please quick.
Hi there, Peter Clark from Innovate UK Business Connect. I'm monitoring the online chat, and we have a question from Paul Williams of Sargentia Innovation, who wants to pose the question to the panel around to what extent do micro and nano nuclear reactors fit into the mix when we think about the SAF opportunity? I'm not sure you've specifically mentioned those types of reactors.
We haven't. I don't know if anyone wants to take... I can, but I'm biased. Go for it, be biased.
So Rolls-Royce PLC are actually developing a microreactor as well as the small modular reactor program. The value proposition of that is that it's deployable, and so you can put it where you need it in the remote situations. You can move it. So when you have those transient demands, you can power that. It's not designed to be the cheapest cost of electricity that you can get because that is achieved by a scale. So it's competing for a different use case. If that helps.
Thank you. Do you want to?
I'd absolutely agree with what Mike said there. It's a different use case, and the reality is PTL requires an awful lot of energy, and so PTL is we think really well suited to working with those sort of mid-scale small modular reactor level of energy generation. Micro and nano reactors are suited to where you need remote access to energy, remote access to reliable energy. And the cost associated with that is higher energy costs because of the value proposition.
Okay, thank you. So one more question over here. I think you've had your hand up. Apologies for quite a while, and then we'll go to summarising comments.
Thank you. Just one quick question for Tim, actually, who I think was probably just reading my mind because I was going to mention the Stern Review. And my question is, have we missed a boat here? Because I assume the technology was available to do small modular at the time of the Stern Review. If we now, when will this come online? Because if we're missing tipping points now in climate change, would it be an investment that is basically just sinking money? Because if you can't change the climate now, if it's going to take 10, 20 years before this technology comes on stream, have we missed the boat?
No, I don't think we have, but I think we shouldn't forget, we need to remind ourselves at every occasion of the longer-term impacts of climate change on the economy. And that while spot pricing is important, the consumer wants to know how much their gas and electricity is going to cost, or how much it costs to fly to America. I appreciate that. But we should start to look at business cases for large technology, whether it's nuclear, whether it's something else, and embed the kinds of Stern Review predictions on hits on GDP. But unfortunately, I can afford to say this easily. I'm an academic. The taxpayer pays my salary, not the profit of my company. On the other hand, I do, wherever I can, remind people that if we don't do anything about it, our GDP could plummet. 20% was a prediction in the Stern Review. So I think if we could start to build in business cases that take into account the longer-term impacts of climate change, not just the physical impact, but the economic impact, then I think that we'll be on the right path, because the technology is there.
Okay. Thank you, everybody. We're running over now, despite my attempt at keeping impeccable timing. So everyone will be hungry. So I'd like to invite the panellists to just have one last final reflection on the discussion, and then we will go and have lunch. Thank you. Robert, do you want to take the mic?
Thank you, Caroline. Yeah, I think I talked to multiple conferences. The fact this is non-nuclear is awesome. To me, it's that engagement and education piece. We are all aware of the emergency this planet is facing. We are aware what we did during COVID. That was an emergency. Look what we achieved as a globe. For me, this has been an awesome conversation. Let's keep the conversation live. Let's keep talking. Please go home to your own companies, to your family, and keep discussing what you've heard today and what you've heard about nuclear. That's my takeaway. Keep talking.
Thank you, Robert.
And yeah, we firmly believe nuclear can solve a lot of the problems in the hydrogen and SAF industries. And so, yeah, we're here for you. I'm here all day. Please speak to us and learn more.
Thank you, Mike.
I'll be brief, unusually. Nuclear, SAF and hydrogen is a marriage made in heaven, I think.
I like that. Thank you. Alan?
I think just to pick up on that final question, at scale solutions take time, but we need big scale solutions and big scale thinking if we're going to make a significant difference. And this is a real opportunity with nuclear enabled SAF production.
Thank you. So I'd just like to thank the panellists one more time. And thank you very much.
Airlines and aircraft makers are desperately searching to reduce their climate impacts. CO2 emissions amount to about 2% of the global total and 7% in the UK, and are increasing. But there are other impacts, such as the damaging contrails. Back in 2011, I was granted a patent for a novel way to generate power and hydrogen from hydrocarbons. Highly efficient fuel cells and electrolyzers make this possible. Using this patented process as a front end to a more conventional gas to liquids process, we can turn all sorts of worthless waste into high value fuel, help clean up the environment and solve the problems of disposal in one fell swoop.
Making sustainable aviation fuel in sufficient quantities is a massive chemical engineering challenge. We've already started building our bench scale system, which will just prove the concept. So we'll take some waste, which is our feedstock, and we'll create some fuel to demonstrate that the process actually works. The key step is then our demonstration system, which will be a 5,000 tonne per year plant, and that will be a very faithful reproduction of the larger scale plant that we're going to scale up to. Then we're going to scale up to our 30,000 tonne per year commercial plant, where we're making fuel, selling the fuel and making money for the business. Jet fuel is a tightly regulated product. In our case, we have to meet those requirements, but we also have to meet the requirements that it's sustainably produced.
Reducing global temperatures and protecting our planet is a key generational challenge. Our mission at Aviox is to deliver the world's most technologically advanced refinery, making sustainable aviation fuel. We believe that the plant will be highly profitable due to the very low cost of the waste materials as input material. We need the resolve and the capital to make a radical shift within our economy to make it modern, circular and sustainable. This is a once-in-a-lifetime opportunity to join a new wave of clean tech companies developing clean, green and sustainable aviation fuel, and it's a privilege to be part of it.
Ready? Okay. Right. Good afternoon, everybody. Thank you very much for attending this session 3 in this 2 days event. We're going to be spending some time this afternoon for the next hour talking about the current status of the fuels approval process and where fuels are in that process as they're going towards approval. And then we're going to spend a little bit of time talking about some of the support activities being carried out in universities to try and accelerate the steps that potential fuel candidates have in getting into the fuel approvals process. So it gives me great pleasure to welcome the 3 speakers who are joining us today, and in reverse order, and for the one who's on stage, Dr. SNL Borzi from the University of Sheffield. And then online, we hopefully have two speakers. I can see them now. First of all, Josh Hine from Washington State University, and then second, Anna Gabrielanin from the Federal Aviation Authority. So welcome. We can see you on the screen, Josh and Anna, and hopefully you can hear us fine. Excellent. Okay, so as I said, I think that was the reverse order of which we're going to see people talk. So in order to kick things off and get an update on the current state of fuels going through the approvals process and the scene of the ASTM D4054 process, I'll hand over to Anna, if that's okay.
Hi, sorry, can you hear me?
We can hear you, yes.
Okay, great. Hi, everyone. My name is Anna Gabrielian. Like Simon said, I work for the Federal Aviation Administration. I'm a part of the Office of Environment and Energy, and I'll be giving an update on the candidate fuels that are going through the D4054 process. So officially, we call them synthetic aviation turbine fuels. We actually don't call them SAF, because in the ASTM world, we don't look at sustainability, we look at safety first. So from a bird's eye view of what we're doing, rather than going into the details first, I want to talk about the U.S. aviation goals for SAF. So when we look at this chart on the right, we see the different mechanisms that we use in order to reduce greenhouse gas emissions, in order to meet a goal of net zero greenhouse gas emissions by 2050. And if you look at the green wedges, those are what would create the largest reduction when the adoption of SAF is used. So in order to help achieve that, we created the SAF Grand Challenge, which was announced in September of 2021. This was a White House announcement, and it created the goals of creating 3 billion gallons per year of neat SAF by 2030, and 35 billion gallons per year of SAF by 2050. And a mechanism that we have in order to reach those goals is the Ascent Center of Excellence. This is our university grant program that we have throughout many different universities across the nation. And that's where we have a lot of different SAF research topics. And this is also something that we have spearheaded with a lot of different agencies, including actually agencies that are foreign. So you can see Transport Canada there. Like I said, we have a lot of different Ascent SAF research topics in our portfolio: feedstock cultivation and land use, supply chain, fuel combustion characterization, pre-screening, materials compatibility, and the U.S. clearinghouse, which is what we use in order to perform the ASTM D4054 process and to help out with that. So the process starts like this. It's 2 phases. The first phase is gathering data in Tier 1 and Tier 2 testing. So that's specification properties and fit for purpose properties. Those are then put into a research report and delivered to a panel of OEMs. This process between the OEMs and fuel producers can be super iterative. So the OEMs may have comments, which then go back to the fuel producers. There could be more data. And that kind of leads into our second phase. Once that first report is kind of reached a consensus, if the OEMs deem it necessary for further, like more extensive testing in the form of component rig testing and engine APU testing, they may do that second phase. And then once consensus is reached there, it will go to FAA review and then to the ASTM world in order to reach ballot and to become an annex. So I'm here today to talk about that FAA step. And I'm sorry if they're going a little slow. I think there's an automatic setting for the next step. So I'm going to go ahead and and kind of reverse some different steps. So earlier I was talking about the Ascent Center of Excellence. In order to like house the U.S. clearinghouse, we have Project 31, which is titled Alternative Jet Fuel Test and Evaluation. It is at University of Dayton Research Institute, where the principal investigator is Dr. Zachary West. And there are many different entities that are our cost share partners, so different fuel producers, different original equipment manufacturers. So the research approach for this project is really to carry out that D4054 process, conduct fuel property testing, support those big extensive testings in the form of engine and rig evaluations, coordinations with the OEM panel, and of course with the goal of creating a D7566 approved annex. So this is where we're just evaluating these novel jet fuels that the industry hasn't seen before. And if we go back to that high level goal of just increasing SAF deployment and SAF use, we're really just trying to enable that supply, because if a fuel doesn't go through this, it cannot be used in the market. There have been many major accomplishments through this project. Most recently, in June of 2023, we had 2 different ballots go through. So first was Annex A8, which is an alcohol to jet synthetic kerosene with aromatics. That was through Swedish Biofuels. And Global Bioenergy's isobutene synthetic paraffinic kerosene, that was approved under Annex A5. So we just continue to do that testing, and that is really our future work. Our future work is to continue what we're doing currently. Gather that data for fit for purpose properties, specification properties, going through research reports, getting consensus through that OEM panel, and sending it off to ASTM for ballot and approval. Okay, so here I'm talking about the qualification status, like what are we actually up to currently? Before we start the D4054 process, we start with initial discussions with different fuel producers. So currently we're talking about different conversion processes such as hydrothermal liquefaction, pyrolysis, and using isobutylene. In the tier 1 and tier 2 step of the process, we have 4 different main fuel, I'm not going to say fuel producers because there's actually many here, but for CSIR IIP, they are a fuel producer. They're creating a HEFA with a larger amount of aromatics in their synthetic kerosene. There's plastics to jet, which is a pyrolysis oil that is being spearheaded by OMV. There are 3 major companies that are looking into creating methanol, creating a jet fuel from methanol. So that's Exxon, Topsoe, and UOP that are creating that task force. And there's also Revo, which is creating a synthetic paraffinic kerosene with a higher amount of cycloparaffins in it. At the tier 3 and tier 4 stage of the process, we have the cycloparaffinic kerosene, which is nearly all cycloparaffins from Shell. That's placed on hold right now because Shell has told us that they need a different partner in the industry to help them carry out that development. And at that ASTM balloting stage, we have Virent with their synthetic aromatic kerosene with a very high amount of aromatics. So we're actually waiting to see what happens there with that balloting process at ASTM in June, which will be in Austin, Texas. And so what has actually already been annexed is these 8 different annexes. So those are a part of the D7566 specification for synthetic blend components, which when they are blended at the correct percentage will be qualified as jet fuel under D1655. So within D1655, we look more into co-processing. There are task forces here, one in order to increase lipid co-processing from 5% to 30%. There's also a task force that's looking into pyrolysis oil from tires, so that's TPO to jet, and also looking at hydroprocessed biomass to jet fuel as well. So that is the qualification process. That's the qualification status. Those are the candidate jet fuels that are going through the process right now. And I'll take any questions now or later, whatever you feel is comfortable, Simon. Thanks for having me, by the way.
So Anna, we can maybe ask one or two questions from the floor if there are any at this point in time. Just put your hands up. Yes, there's a gentleman at the back there. While we get a microphone, please, go ahead. While that's happening, Anna, can I just ask a quick question? You showed the status, the position, or the position where various fuels are in the process. Could you give us an indication of the amount of time that it can take to get through that process, and also the volume of fuel that's required?
Right, that's a good point. So we usually expect 50 to 100 gallons of fuel before a fuel producer enters the process, and that's really to show that they're ready to deploy this fuel. Because if we receive something on the order of milliliters, that could be anything from just a very demonstration fuel. So we're really looking to make sure that the resources that we have for the D4054 process are going towards fuels that are going to hit the market. Especially like relating to your first question, the amount of time and effort that it goes into qualifying one of these fuels as jet fuel can be extravagant. And to give you an answer, they're all unique. They're all unique in their own ways. They all got their own personalities, and so they can take months to years, and that really just depends on how novel the fuel is, how different is it from what we've seen currently in the current jet fuel.
Yeah, thank you very much. Okay, there was a question at the back as well.
Thank you. Can you hear me? Yeah. Thank you for the presentation. It's very, very clear. Just a question about the ASTM ballot process. How often does that take place? Is it once a year, or is it more frequent than that?
It's more frequent than that. In person, it's twice a year because they work on a semester system, but they take ballots monthly.
Okay, thank you.
Okay. And we have another question at the front here. And then maybe we'll give Anna a break and move on.
Thank you very much for the very technical presentation. My name is Vincent. I work for 270. We're an aviation consultancy company. I asked the same question to your fellow clearinghouse, if I can say it like that, the UK clearinghouse, which is in development. I'm wondering if you have fuel properties available for the fuels that you have tested and have gone through ASTM approval in terms of things such as aromatic content and hydrogen content, and if these are available at all for governments or other organizations that are looking to understand potential non-CO2 impacts of these fuels.
Right. I would suspect that, I know that information is in ASTM research reports, and especially when those are published, if that like once that goes to ballot, then that is known by the general public. Before that, it's kept internal.
Yeah. So there's a variety of sources of data that are for jet fuel specifications and properties that are both public and some that are that are private and are more behind some firewalls, or either with payment or more restricted than that. So there's a wide range of different sources out there, And we can, maybe when we get to the question and answer session at the end, we can list a few of them for you and give you some guidance. But I think, because I'm sure Josh will mention it as well, and Ehsan will too, so that it's a common theme. But before we move on, we have a question from, or a comment from the UK Clearinghouse.
Yeah, I know, it's Chris Lewis. For people who don't know me, the director of the UK Clearinghouse, although they should know me by now. Yeah, just to answer the question, I think once the reports have been encompassed and everything's been approved, they are actually quoted in D7566, because each annex, and indeed a lot of the research reports in the front of 7566 and in each of the annexes, the actual reports are, you know, the reference for those reports are quoted. I think I'm right in saying that. Is that right, Anna? So people, if you get hold of a copy of 7566, and then you would have to, you could apply to ASTM to get copies of them.
I believe they're also on the ASTM, is it called Compass online portal?
Yes,
Yes.
there probably are as well. So, but you have to be an ASTM member to do that. And there's a guy, and I can't remember his name now, who says people who are not ASTM members but need access to approach ASTM, because it is, you know, it's a you have to be a member to get on the system. But we can help you with that. So sorry to interrupt, Anna, but I just thought it was useful to, because it was a question that came up yesterday. It's a lot of really useful data there for people.
No, I do appreciate it, Chris. I think they might also have to be purchased. I'm not sure, but I think Josh has something to add.
Yeah, so yeah, thanks, Chris, Simon, and Anna. Yeah, just to follow up with that, the Compass report on Compass, ASTM Compass, you can go and get all the ASTM research reports for all the various annexes, and you do have to purchase them. Another resource that Simon was kind of hinting at that may come up later, but there's multiple other databases by individuals, and Simon may be able to point you to one more locally, but there's also one at the University of Illinois. There's an alternative jet fuels database that has a lot of these properties on there that you don't have to purchase, but you do have to sign up through a website to get access. So those are two resources.
And to plug one other Ascent project, there's Ascent Project 90, which is the World Jet Fuel Survey, and also done by University of Dayton Research Institute and Dr. Zachary West. He's asked for different samples from around the world of current jet fuel to see what does jet fuel even look like right now.
Yeah, so just to add to that, there was a survey done by the CRC, the Coordinating Research Council in the US in 2000, well, it was published in 2007, and that was the last global survey of fuel types, and that kind of information you're getting at is in there. But as Anna says, we as a community are currently in the process of updating that. So in the near future, there will be a new version of that report.
I don't think I've ever gotten such an extensive answer to a... Thank you.
And we've barely scratched the surface. We can keep going. So, okay, thank you very much for your questions, and thank you very much, Anna, for answering. We're going to slowly shift focus now to away from the formal approvals process to look at the something that we have been calling pre-screening, which is essentially an activity to try and streamline a little bit the approvals process. As Anna was saying, there's quite a lot of quite a high volume requirement for small-scale fuel producers at the early stages in producing a jet fuel product, and potentially quite long timescales to get through the approvals process. So for those producers who are making or intend to make fuel that doesn't already fit within an annex, there's quite a high threshold for getting started. And Anna correctly pointed out that some of that is almost a good thing, because you have to be serious to enter into the D4054 process to want to manufacture a fuel. But if you're wanting to see how your fuel measures up against the specification and against the standards, we felt several years ago, along with a variety of colleagues, including Josh, that there was a bit of a gap, and the universities could play a role in supporting that activity as candidate fuel producers start to approach the point at which they want to take part in the formal D4054 process. So in order to give a bit of an overview of some of the activities that we have been doing, and in particular Josh has been doing at Washington State, I'm going to invite Josh to give his presentation on the pre-screening activities that he's undertaking and give you a bit of a flavour of the type of things that are done. Josh, the floor's yours.
Excellent. Thank you very much, Simon. Thank you very much for all of you in the audience. I wish I could be there. Been in DC this week for some other SAF-related activities for FAA-funded projects, but really very grateful for this opportunity to speak to you all. So as Simon was saying, and as Anna mentioned, the barrier to entry to ASTM D4054 for official qualification is quite high. Anna mentioned somewhere around 50 to 100 gallons is required to enter the process. And from what we have heard from multiple producers over the years, that level of volume scales with roughly $100 million of investment. So getting that type of investment to enter the process is pretty substantial. And so what we've been doing over the last probably 6 years at my previous institution, University of Dayton, and now Washington State University, is to try and accelerate the development of various novel SAF technologies called through pre-screening. I'm going to give a little bit of advertisement here for where I'm from and some of the stuff that we're known for. I'm the co-director of a joint institute with the Pacific Northwest National Lab, or PNNL. It's a joint institute where we basically share 4 different things, be it people and like staff. So we have joint appointment programs where WCU folks can operate as PNNL staff and vice versa. We have a joint graduate program, and we have a shared space. And I want to highlight the shared space because if I had a laser pointer, I would point to it, but it's effectively somewhere in the middle of that that first floor, in between 2 of those different flags. That's where the 5 gallons for fit for purpose testing for the alcohol to jet pathway were developed. So PNNL has a patent there that LanzaTech and LanzaJet use. And there's a lot of SAF conversion activity that goes on in this building. And it's also now where we have our SAF testing facility. Let's see here. All right, so as Anna mentioned, there's several different tiers to ASTM D4054. And what I'm illustrating here is there's really this pre-screening tier of testing. There's 2 tiers to pre-screening testing that we've defined them as. There's a tier alpha and a tier beta. Tier alpha is analytical chemistry combined with property predictions. So that requires somewhere in the order of a milliliter of less. We've gotten samples that we can barely get 1 GC injection into our system. So we can do pretty low volume testing there. And then as producers are producing, somewhere between 30 and several hundred mils, we do this, what's called tier beta testing, where we actually test properties. Over the last 6 years, we've been selective in terms of what equipment we've purchased and really focused on, very low volume, high fidelity test methods and equipment. And so we're able to do or squeeze a lot of tests out of relatively modest amounts of volumes over the years. There's quite a lag here on the slide advance. So what we do, I'm going to have, apologize here. So what we do a lot of right now in the lab is this pre-screening, helping various entities enter the qualification process and educate on many of these different aspects. And so what we do is we receive Initially, very low volumes, milliliters of material or less. From a producer, they're at the top, line 1. They send us samples. As Anna mentioned, the 4054 process can be iterative, but the pre-screening process as well can be very iterative. So we have received sometimes on the order of several dozen samples from various institutions as they optimize their process at various scales. And then at a certain point, once the producer kind of understands the process and the implications potentially of their fuel properties and composition, we move forward to introducing them to a select group of OEMs. We work very closely, and I have a leadership role within the Commercial Aviation Alternative Fuels Initiative, or CAFI, which is a public-private partnership based in the US, but we have many institutions and individuals from abroad join us in this effort, CAFI. There's a brief presentation by the novel fuel producing company where initial data, commercialization plan is described, and then a pathway is all presented. And then at that juncture, the OEMs may, or others involved in this presentation may ask for additional tests. There's a more public presentation that's sometimes given after that. And then at some point in this process, an ASTM task force is developed. And all throughout this process, we'll receive additional materials of larger volumes as the institution scales their technology. And then at some certain point, I think this horizontal red line is a little bit subjective, what you describe as the official D4054 entrance, but somewhere around submitting the final, the 50 to 100 gallons of fuel, the more formal process begins. We currently have received well over 220 unique samples from more than 36 institutions across North America and Europe. It's a bit less than $2,000 per sample. We get materials processed sometimes in the order of a couple weeks or less, sometimes in a matter of hours, depending on the urgency of certain things. We have dozens of material transfer agreements and non-disclosure agreements. This can take some time if you're interested in getting testing done right now. And our tier beta tests right now, we can do them with about 30 milliliters of volume, and you can see the properties listed there. The properties that we focus on, I didn't mention this previously, but the properties that we focus on under tier beta are the most important properties for the largest scale testing done very late in the qualification process. So what we're screening for predominantly is the bulk compositional properties that are going to be the biggest issue for operability testing later on. There's other trace contaminants and other things that are tested sometimes at this pre-screening level, but not necessarily every single time. You can see the last two tests there, the Jeff Todd and derived cetane number, are the biggest fuel hogs that we kind of include in this tier beta testing. But sometimes for some pathways, those aren't always requested by the OEMs. In terms of how we do what we do and how long we've been doing it, in some sense, the tier alpha property predictions really go back to surrogate work that was done about 15 years ago. I'm highlighting Steve Dooley, who is now the EU clearinghouse director. So Steve and I have been working together for many years now. We've written a book on operability effects and fuel properties and so on and so forth relative to alternative aviation fuels. And so what we basically do is we're able to do very low volume testing and predict many different properties. We have roughly 35 different properties we're able to predict with around a milliliter of sample. And the way that we predict those properties is using multi-dimensional gas chromatography, or GC by GC, coupled with FID and VUV. The VUV is able to identify stereo and structural isomers when we have those data in our database, and leveraging that information, we're able to predict properties much more accurately. So this lower left plot is illustrating a GC-GC tier alpha prediction without any stereo or structural isomer information in the blue. And then when we couple that to VUV absorbance spectroscopy, we're able to predict things much better here. This is viscosity versus temperature, and viscosity at low temperatures is a very important property for operability concerns. This is a chart that we basically put together for every pre-screening sample we receive. We focus on testing compositional properties and physical properties. What I'm illustrating here is a candidate fuel, the hydrocarbon type distribution for that candidate fuel, which is the color map colors in the percent mass versus carbon number plot. The green background is an average Jet A. And so, you know, the closer to this type of carbon number distribution and average carbon number, the less risk many times OEMs will perceive in a candidate fuel. You don't necessarily have to match this identically, but it is a pretty good metric to understand what kind of risk a novel technology may have moving forward as perceived by the OEMs. We also do all these are the main tier beta test properties. So here what we're illustrating is various physical properties that are important for operability. Again, the green shaded region represents a conventional fuel range. Red lines and shaded regions are out of the spec. So while this particular candidate fuel may be low in terms of the density, this is a pretty common trait for what's called synthetic paraffinic kerosenes. So at a blend, it would go back into the green. That's not an issue, but we screen for these properties and kind of, you know, communicate, you know, how things on the compositional side of this plot impact the things on the physical property side of this plot. And that sort of information can be coupled into the novel conversion technologies and feedstocks of new SAF producers. This is something we've been spending a fair amount of time on recently on Pareto optimal distillation cuts. So, you know, distillation cut is, you know, it's a very, people who've been working on it for a long time, but it turns out that because you couple a novel feedstock to a novel conversion technology, the distillation cuts for SAFs can vary a bit more than what you would expect from conventional fuel. And the amount of yield, or the amount of carbon that you get from your SAF technology, the amount of yield that goes to aviation, can play a really important role in the financial models for various institutions. And so squeezing out as much carbon into the aviation cut is a high priority for many different institutions we work with. So what we're showing here is on the inset A on the far left is a carbon number distribution from a SAF producer that they sent us pretty immediately out of their process. And they asked us, you know, what's the optimal distillation cuts? And so we did our typical process, which is now illustrated in the blue bars in B of that inset, the next plot right next to it, and tested the properties. And you can see those properties down the middle, and they look quite promising. This was part of a larger campaign that we were working with this particular institution. they sent a much larger batch of volume to another place, and they got quite a bit different result because the distillation cuts were different. So one of the things I just want to illustrate here is that you can see that for the orange distillation cut, the viscosity is almost at the extreme limit, which is a concern. So, you know, while the distillation cut for the blue was much narrower, and you would think intuitively that more conservative cut would give you better properties, it turned out in this case that was not true. Our SAF yield also had about 36% more yield than the orange cut. So a lot more carbon going to SAF, and actually a lot better properties in this particular case. I don't want to give the impression this happens for every SAF route, but for this particular one, that this was the case. So I want to thank you for your time. Happy to answer any questions. I encourage you to check out my Google Scholar page. It has a number of different publications in terms of prediction methods and so on and so forth. So thank you for your time, and thank you for the opportunity.
Thank you very much, Josh. Let's give him a round of applause. So Josh, really encouraging to see a really good example there of how you're working closely with a fuel producer and then tailoring or seeing how you can maximize the amount of carbon you're getting into your product. Just a quick question from me, and if there are any questions from the floor, we're happy to take them. Josh, you mentioned fuel samples, and we were talking about samples in a database earlier. I wanted to ask, what happens to your fuel samples that fail the specification or fail the testing? Because they're really interesting to help you build and develop your modeling capability and understanding of the fuel chemistry and its impact on fuel properties. Do you have many of those? What do you do with that information, and is it shared more widely? Or?
You know, like I said, a lot of the tests that we perform are under NDAs and MTAs, and so there can be quite a bit of variance in terms of what is in those material transfer agreements and non-disclosure agreements. You know, we've had papers with producers that disclose a lot of information on their technology, process, and properties. And, you know, in that other example, you know, that's an anonymous route and an anonymous producer, and that's it. So that's the level of detail we can share in that case. But yeah, you know, there's a couple things, you know, that we've learned over the years. It's surprising how sometimes water can get into some of these samples. So the graduate student that does a lot of this test just puts it in a pretty standard freezer immediately when we get a sample from a new producer, and we can see water sometimes at the top, and that's a pretty quick, cheap test to inform things back to them. But yeah, leveraging the data for a lot of the prediction stuff, you know, we've been getting better at it, but there's a lot of data. The VUV, you know, files are gigabytes, and so there's a lot of information there. But yeah.
Thank you very much, Josh. Are there any questions from the floor? Or online even? No? Okay. Well, Josh, thank you very much for your presentation. I hope it's been interesting to hear your progress and see some examples. So thank you very much. I'm now going to hand the floor over to our last speaker, Dr. Ehsan Alborzi. So Ehsan, you're going to be talking to us about some, please go, modeling capability to try and bridge the gap that, as Josh was alluding to, between the knowledge of the chemistry and the composition of the fuel and its performance properties. Ehsan.
Good afternoon. I'm Ehsan Alborzi from Sustainable Aviation Fuel Innovation Center at the University of Sheffield. And today I'm going to talk briefly about the challenges we are facing with one of the properties, the relationship between permittivity and density with respect to the sustainable aviation fuel or synthetic fuel. So we know that the role of sustainable aviation fuel for in net zero 2050 is something that we agree on. But there are some consideration in terms of safety and also technical suitability makes that these fuels need to be carefully assessed, characterized. So these blend ratios are typically fixed by the differences in the properties between the conventional fuel and SAF fuel. An example of the challenges that we are facing with respect to these density and dielectric properties with SAF, I'm going to briefly talk about it in this presentation. So permittivity or dielectric, so there are two equal terms, is one of the fit-for-purpose property, so is not controlled by the fuel specifications. So it requires further research and elaboration. So very quickly, I'm not going to go to the detail of how the fuel gauging on board is taking place. So usually fuel quantity fuel quantity indications uses probes to measure capacitance changes. So there are several probes located in each fuel tank, each different parts of the aircraft, and each probe should provide a capacitance. And the variation of the capacitance is proportional with the level and height of fuel in the tank. So, what capacitor is? The capacitor is a device for storing electricity. And as you can see here, the amount of electricity depends on area of the plates, the distance between the plates, the material between the plates, so it could be either jet fuel or air, and the material between these two plates, they have some serious effect on the value of the capacitance. So fuel mass, in order to calculate, in order to estimate the quantity of fuel on board, we need mass of fuel, and mass simply is given by volume and density. So volume is usually calculated through some specific algorithm like fuel height, tank model, and fuel surface attitude, and also density can be either measured or derived from other data, from other quantity, which is a dielectric. So, but most of the civil aircraft, they use on the driving or inferring density from the data. How we can drive density from dielectric? Typically, there is a graph, there is a way, there is a linearized function between the dielectric and density, known as Clausius-Mossotti. So in this graph, K represents permittivity or dielectric, and D is density. As you can see, conventional fuel pretty much follows a straight line. The one is indicated there, and there are some research by Airbus, ARINC, which indicates that the conventional fuels follow that straight. But moving from conventional jet fuel to more synthetic fuel, we can see some shifts, some differences from the linear behavior. And this is one of the challenges. This is one of the challenges that we face with the blend of SAF in conventional fuel. And the accuracy for the calculating the fuel quantity is central. So central for the flight. So an error margin of 5 to 6% is usual, and around 1% is desirable. But shifting from this linearity presents some challenges. This graph shows the fuel chemistry between the differences between fuel chemistry on a Jet A1 fuel on the left-hand side and a CHCJ fuel. And obviously, it can be seen, it can be observed that different proportion of the chemical constituents and different amounts of them may be a bit of problem when we are talking about the behavior of the fuel and requires further research. So, we had an interlab study. I have to say that ASTM D924 for dielectric is not applicable to jet fuel. And UK Energy Institute approved a new test method known as IPPM FC21, which was, and the device was manufactured and designed by Stanhope Sita, and Sheffield University was part of an interlab study with other 8 labs looking at different fuels. And we looked at the functionality and reliability of this device. It's known as JetDC, and it measures density and dielectric over a range of temperature simultaneously measure density and dielectric for over a range of temperature. So what we wanted to do as a fundamental research at the molecular level, because when people looked at the behavior of cycloparaffinic components in aviation fuel, they believed that the shift from the linearity in closest osmoticity is due to the behavior of cycloparaffin. So we decided to look at these groups, these classes of hydrocarbons in isolation and also as a blend. So we looked at the normal paraffin, isoparaffin in the range of C6 to C18. Cycloparaffin and aromatics we haven't decided yet because these are a bit tricky components. And the different ratios of the above in terms of binary, ternary, and also 4 components. So experimentally, we are limited. We are limited by available resources and by available materials that to cover all chemistry for the jet fuel. So we decided to use a combination of molecular modeling and experimental work. So in molecular modeling, I'm not going to go through the details of molecular modeling. We used a technique known as molecular dynamic simulation. With that, we calculated the properties, density and dielectric for a wide range of chemicals. And this technique is computationally a bit expensive. So we use high computational center at the University of Sheffield. So each calculation for each molecule, on average, using CPU, 32 CPU core, 32, and also memory of 200 GB, it takes more or less 3 to 1 week. And the results are shown here. So first, we had to validate our MD results, molecular dynamics result with experiment. So what you can see on the left-hand side is the density at 20 degrees in terms of carbon number. So we have a very good agreement between calculated values and also experimental, and for some of them which are available in literature. Also, dielectric showed a good agreement. The calculation for the dielectric showed a good agreement. And also, we extended our calculations to the ISO components. And as you can see, density show a very good agreement with the experimental result. With dielectric constant, we had a bit of problem, and these calculations can be improved if we elongate the computational time. So, what happens? If we plot the density and dielectric in terms of carbon number, like C5 to C16, you can see the trends are nice and predictable for both density and dielectric for normal paraffin, isoparaffin, and cyclo. I have to say that isoparaffin in this case means a chain of carbon number and a methyl attached to the second carbon. And the same applies for the cycloparaffin. However, moving to the iso components, we can see a shift in trend. You can see we are not quite, okay, so I have to, for those people who are not familiar with SMILE structure, SMILE is a notation by which we can present in a chemical and understandable for computers. So what you see here, CCCC are a chain of carbon, and what is in bracket, they are branched attached to the same carbon number. So by, in this result, you can see that looking at the iso components for density, there is a shift from linearity, and the dielectric component, constants for very same chemicals show more or less the same trend. And when we are moving to density of cyclic attached to or bonded to methyl group, we can see a trend and some irregularity, which I'm not sure, they need to be further investigated why in the last bit that things happened, that irregularity. And for the effect of, the calculation for the cyclic, for the permittivity of cyclic component show more or less the same trend, but with a lower slope for the dielectric, for the cyclic component. When we move to the plotting all of this in the form of Clausius-Mosotti, we clearly see that the behavior of the normal paraffin, isoparaffin, and cycloparaffin, they cannot follow the same trend. So that clearly indicates that the chemistry of fuel need to be carefully investigated, carefully established by techniques like chromatography, and this research requires further work to look at the different blend ratios. So the conclusions that I'm going to take from this presentation is when these calculations, when these properties are presented in the form of Clausius-Mosotti, trend of N normal isocycloparaffins are dissimilar, and the effect of branching is very important for both iso and cyclo. Such a deviation from linear behavior in Clausius-Mosotti form needs further study for mixtures and blends, and also over a wider range of temperature. And if the deviation from linearity continues, so low fidelity model like correlation between density and dielectric is not valid anymore, and we need to move towards higher fidelity models like application of the neural network or machine learning. And finally considering the changes of density and variation of chemical composition for every type of prediction that we need with a high level of certainty, we need a clean and novel set of data. The data need to be clean and reliable. So in this work, the main intention is to create a novel set of data and build our predictive tools based on this data for a blend of fuels. Thank you very much.
Okay, thank you very much, Ehsan. Do we have any questions from the floor for Ehsan? Or online? Okay, well, in the interest of time, Ehsan, I think we'll sort of draw things to a conclusion here, because we'll run the risk of having you late for the activities in the other room if we carry on for too long. So hopefully that's given you a bit of an overview of some of the current activities in the fuels approvals process, and then a bit of an insight into some of the pre-screening and property prediction activities that are going on. As we finish, we should say that's a very big topic to cover in an hour, so there's a huge amount of material and content. If you do have any questions and want to chat with any of us now or at a later date, please do get in touch. We're quite happy to talk about this, and we're a very open community, including Josh and Anna, and we should say we mentioned as well Steve Dooley at Trinity College in Dublin, and the team at DLR in Stuttgart work very closely on these activities together. We're quite happy to for you to get in touch with us outside of the room. So thank you for your attention, and we'll draw things to a close there. Thank you.
Thank you.